Right. He's also from same 87 batch.
87 batch.
Yeah. BTech Computer Science. Yeah. And he also actually studied in Badaयूं.
Okay.
He's not from this. Yeah. He's not from my hometown, but he studied there. Okay. Sorry. All right. Fine.
Yeah.
Why is it doing screen mirroring? Nope. What did I do? Yep. Are we good? Good? Okay, all right. Morning, everyone. How are you guys doing? Good? Okay. So, day 9, right? One more day to go. Have you guys learned something so far? Yes. Okay, good. So, what we are going to do, I'm not asking the questions where did we leave yesterday, because today we are going to do applications, right? And as I mentioned that I'll pick 2 examples that some of you had suggested or asked for or showed that that's the area in which you're interested or you're working. So we're going to do that. So overall, 3 different use cases that I'll pick up or examples. Majority of them, 2 of them are 2 application domains. So you're going to see how exactly whatever we have learned in the last 8 days, you'll see a lot of common terms. You'll see how exactly you map those into problem areas. So 2 of them are studies, literally in a way, published work that describes the project or work that was done. Should be easy to replicate, because both the papers I picked up were such that if you want to test them out, you should be able to test them out as well. Third one is because a couple of you had interest in figuring out if I want to design the LLM, how exactly we're going to do. So I'm going to go over the steps and processes. There are a couple of different frameworks that you can use which provide you building blocks so that you don't have to really start from very scratch, i.e. You don't need to really build a neuron first or a perceptron first or implement the backpropagation algorithm or feed forward. All of it is now available as part of libraries and frameworks, so it's not that difficult to experiment with building some kind of a language model or a network, right? So we will talk about that towards the end. Okay. So we'll look at some applications, key technologies, in a way that whatever we have done or learned so far in the last 8 days, we'll continue to focus on that. So first example I'm going to take would be if you are going to build a chatbot or a dialogue system. So how exactly you go about it. Now the reason I'm using this is this predates the neural networks. Theoretically speaking, you can build a chatbot or a dialogue system without ever using a neural network system. As a matter of fact, very first example of AI, and I refer to that, the name ELIZA system, was written without having any idea of how neural networks work, what's deep neural network, etc., right? The idea there was that it has to pass the Turing test. We talked about Turing test, I think either on the day 1 itself or maybe on day 2. Right? So you could write a chatbot without ever really implementing or considering the neural networks at all. So we're going to look into the two different ways of building the chatbots. I am skipping the math part, but you know the basic math basically, but we'll see how you take a problem, map it to the tools or techniques that you know, and then figure out the solution, right? So that's what we're going to look into it. Let me just say this, any questions at this point of time from the areas that we covered yesterday, because today we're not going to talk about any of those, but you can think about some of them as we look at each applications, right? So if anybody has any questions from yesterday. No? Okay. All right, let's start with a chatbot or a dialogue system. Is there anyone who has never interacted with a chatbot or some kind of a dialogue system? Right, so all of you have, right? Do you have a preferred one or one that you like? Or the other way, something that you did not like? Okay, let me make it easier. Can someone tell me which specific dialogue system or a chatbot have you recently interacted with? Sorry? Alexa. Is that what you said? Okay, anybody else? Eliza B. Where did you find it? Okay. I mean, see, you call a bank, for example. Let's say you have an account in ICICI Bank, right? You make a call. I'll tell you why I'm taking this example, because yesterday I was with someone, they had to make a call, right? It never goes to a human directly. It goes to a chatbot, roughly. Any idea how that chatbot is working? If you have ever encountered this, how exactly it goes? I think first it asks you to pick your language, at least the ICICI one did. Right? Then it says that, do you want to do a checking account, saving account, whatnot, open a new account, etc., right? Then you pick an option, then it goes few more questions, then it goes a few more questions, etc. And finally, either you get it answered, or say resolved, or it says that go back, and there's a third stage as well. Any idea what the third stage is? Frustration. Because what happens is that you wanted to get something done, you spend like 5 minutes following all the options, and eventually discover that that's not what you wanted. Or it says that you cannot do what you're looking for doing it, right? How does that work? This is called a call tree, if you have heard that term, right? No different from the search tree, but what is happening is that you as a user have no choice. I mean, fine, you are given an impression that you have a choice because at each level you are picking an option, but even if you know fully well what you want to do, which in this instance last evening, we knew what we were trying to do, but we couldn't get through the person. And eventually what happened is that trying to get it done online or through the phone system or through the chatbot resulted in actually visiting a branch because we couldn't get it done. The people in branch couldn't get it done. They had to somehow figure out how to get it done. Point I'm trying to make is that chatbot old way had a fixed logic. If your requirement doesn't fit in here, chatbot is of no use, right? So some examples that you may have seen, Siri, Alexa, Cortana. Cortana was one of the Microsoft's chatbot, Google Assistant. They can do a lot of things. They can play music for you. You can just give them instructions and they'll respond to it. You can chat with them for fun. Eliza, when it started, people actually find it very addictive in the sense that it can chat with you forever, actually. I mean, I wouldn't say forever because you do reach this stage. Think of it this way. Any chatbot which is using a fixed kind of a tree mechanism to navigate, eventually you will end up at that stage where you'll say that, okay, it's not making sense. So, but that's a couple of places that you are. Booking travel reservations, usually you will see that the travel reservations, you are dealing with a chatbot. I'll ask you a few questions. Majority of the time, maybe it will successfully make a reservations, maybe not. It is being used for mental health. It is being used to figuring out people who are feeling boredom, more so in the Western countries where there are not enough people available, but increasingly, I assume, in India also. If you are alone, if you want to find someone to chat with, the chatbots are being used to help with not necessarily mental patients, but mental health related issues, right? So there are two distinct type of conversational agents that you can think about it. One is mimicking human chatting for fun, for therapy, or for maybe doing small tasks. The other one are dialogue agents specifically just doing the task-based systems, right? Say, for example, on phone, actually phone I would say both ways. Siri primarily is a dialogue agent for chat, for the task-based. If any of you have used Siri, you might ask it, okay, set me an alarm for 6 a.m. next morning, right? Find out or play music or find a file on my phone or call this person, it will do that task. Generally, they are interfaces. So what is happening is that they're not necessarily doing the task. They're basically initiating the task on your behalf. So if you make a call, hey Siri, I mean whatever is the call word, and then say, do this. It's only initiating that functionality. That app should exist on your phone. So they are acting as an interface. They're usually available in appliances, they're robots and cars, all kinds of things have now a voice-enabled access, so a layer on top of the actual functionality. Flights, booking, restaurant, things like that, right? Two different kinds of conversational agent. As I said, one is purely a chatbot with some functionality for task, and the other one is only specifically related to task. Now look at it, how exactly you design them. One is based on the rule base, which is really the rule tree or a call tree. The other one is corpus based. Now what does that mean? That there is a database of actions and responses. It is not necessarily already structured like a tree, but you have it somehow. And anytime when you are trying to have a communication, it's searching through it. It's retrieving the information, or the last option, neural encoder decoder, which is really using neural network to build a chatbot. Does that make sense? Right? Any system that you're building requires some data. You can call it data, information, knowledge, whatever it is. It needs to be organized in some way, shape, or form. Why does it need to be organized? It needs to be organized because it can be searched easily. If you organized it as a tree, the search path is predefined, right? If you organize it in some other way, search could be more generic, right? On the other hand, if you are going with a neural encoder decoder network, your hope is that the bot can do more than what it is explicitly being told. Same thing that we discussed earlier, that there is a latent space, it discovers information on its own, it can answer the questions even if it has not seen that question before. That's the whole idea, right? So if we continue on that topic, the task-based or goal-based dialogue agent, where you do have a well-defined task, whether it's setting a timer, making a travel reservation, play a song, buy a product, any of those kind of things, make a phone call, which is not there yet. These are called task-based or goal-based system. Now, why they are differently defined? Because it's very straightforward way. Like you need to make a phone call, all that the agent need to do is to search in your contacts that person's name, find out the phone number, and then initiate the call using whatever the phone app you have on your device, right? Their architectures are usually very straightforward because the goal is defined, the intermediate step that you need to take to reach to that goal is defined. All it needs to do is to fill some information or some gaps. Either it can do it on its own, or it will ask you the question to provide this information. So say, for example, I'm trying to make a travel reservation and I say, hey Siri, can you book me a ticket for Delhi? Maybe it will say, yeah, sure. Now it will go to a goal-based system and it will say that, okay, I know the person wants to book a ticket for Delhi. Now it will say that, do you want a train ticket or a plane ticket? Because it will see that one of the frame or task needed is to figure out what ticket. Then it will probably ask for which date. Then it will probably ask for, do you have a preferred airline or something of that nature, right? So that's the task-based or goal-based dialogue agents. theoretically speaking, because you know what is needed to achieve that, you're trying to get that information. So it will look something like this. Frame is the structure or the organization that's called, in the sense that this is the information you need before this task can be completed. Think of it this way. That's a frame for train reservation. If you're trying to make, let's say, purchase a product, or if you're trying to make a phone call or arrange a meeting, book or get a restaurant reservation, the frame may look different. Is that point clear? Right? So basically what you're saying is that you're building a dialogue system which basically has a goal. You could have a dialogue system which can only support one goal, or it may have that it supports like 20 different type of goals. For each of those goals, you define what is the basic information that's needed to be filled. And then the intelligence of the dialogue agent comes in is that how many of these pieces for that specific task can it automatically fill. That could be based on your information that you've already provided, like your contact details. If it says that call my dad, if you have already labeled a contact as dad, it already knows that. It already has the phone number. If you ask it to make a phone call to Barack Obama and Barack Obama is not in your friend list or not in your contact, it'll probably ask the question, what's the phone number for Barack Obama, right? Same way, if you're trying to make a reservation, it says that it needs to know which city you're starting, which city you're going to, what's your departure date, what time, what's your preferred airline, etc., etc. If you have already provided defaults or have a profile set up, it will fill in all this information for you automatically. If not, it will ask you a question, right? Not that very difficult. As a matter of fact, it should be a couple of hundred lines of code, and you should be able to write a chatbot agent provided for simple works. Sending an email, sending out a chat, making a phone call, all of those chatbots things can be prepared using some kind of a goal-based or a task-based model, right? Now, let's say you want to extend this to a slightly different way of communication. There are two different possibilities here. If you think about it, how many of you have used any travel websites? Which one have you used? Make My Trip, right? Make My Trip would probably have a form. That's a usual interface when you're trying to get something done, is that you basically have create a form. So that's one way. You can actually say, I don't need to create a conversational agent. I will just create a form. You just type in what you want, click the button, submit, reserve, book, whatever it is called, and then it'll be done. Behind the scene, it might run some validation. It might see that, okay, you can't be leaving on a date that has already passed. So I'm saying book me a ticket for January 5th, 2025. So there may be a validation saying that, hey, January 5th is already gone. You can't book a ticket for that. Or you can't say that your origination and destination locations are exactly the same. You probably don't need a ticket then, right? So all of this can happen. But in some cases, the company might say that they don't want to give a form as an interface, so it could be a conversational interface. It could be something like this. Not exactly the example of the travel booking, but a conversational agent. Now, if you read through this, let's say, what does it feel like? Does it look like that it has a goal-based implementation, or is it somewhat different? This comes from, again, a published work. I have a reference there, I think 1966. Yes, that's what I was saying. It's 1966, 1960. So somebody else who mentioned ELIZA is probably a variant of this, which is probably available. If you search around, you would find modern implementation for this kind of a conversational agent. These agents, written in a very simple way, can actually keep you engaged for a long time. Now, long time might be few minutes, maybe tens of minutes, but because they're all using some kind of a defined methodology you will end up in this state at some point of time. It will end up asking same question over and over again, or it will get into a loop of 4 or 5 questions where you answer and it doesn't matter what you answer, it keep on asking the same set of 4 or 5 questions. That happens. But anyway, what does it look like? Do you think it is using some kind of a frame structure that I showed earlier, or is it doing something different? Do you realize what kind of technique is this conversational agent employing? Or let me put it this way, if you had to design something like this, how would it go about? How would you go about it? What is it doing? Have a look at it and see what exactly it's doing, or at least make some kind of a educated guess. So if you notice, there are 2 or 3 techniques it's using. You can call it heuristic also, you can call it design elements also. One thing it seems to be doing is that it has some trigger words. So if you say that trigger word, it knows which question to ask after that. If it cannot find a trigger word, it will ask you to define what do you mean by that. If it cannot do any of that kind of thing, right, it will ask the question turned back. You're not very aggressive, but I think you don't want me to notice that. What makes you think I'm not aggressive? Now, that's a pretty stupid question to ask if you want. If you ask me that, it says you're not aggressive, great, that's like a positive thing, but it says, oh, because there's no intelligence here, right? It's either trying to find a trigger word that it knows about so that it can ask the next question, or ask you to define, or just simply ask a counter question. You say that you're great. Oh, what makes you think I'm great? Or what makes you think that I'm not great? Or whatever the question. So that's what it's doing. Now, this is a specific style. If any of you have studied anything in psychology or clinical psychology, there's a specific way of training that psychologists have called Rogerian psychologist, because the work of the psychologist is to understand your thought process. And the way they do it is by asking questions. They do not have, okay, I shouldn't say that they do not have a prescribed set of questions. They have a prescribed set of input that they want from you. But they do not want this to be a monologue, like they ask 5 questions, you give 5 answers. They want to dig deeper. And the way they do it is exactly what Eliza is doing, in the sense that they will take a clue from your answer and then quiz you more about that. Why did you say that? Why did you do that? Why did you not do that? Etc., etc. So what it is doing, the ELIZA, which is right from 1966, that's exactly what they did. So another thing, I would mention it one more time here, because I have an opportunity to do so. If you are doing a research, if you're trying to do something else, look around, see what other fields are doing. So in 1966, somebody wanted to create an intelligent conversational agent. While trying to figure out what's the best way to do it, which is not like a call tree, they thought, why don't we model it like a psychologist? And on that, specifically a Rogerian psychologist. What they do is that they play the patient statement back at them. Sometimes they will exactly repeat the same statement because they couldn't figure out what the next question. They'll repeat the same thing, hoping that the patient is going to say something more. Right? That's the style. You can say that I know nothing about the real world. I'm only going to ask you whatever you say. Let's say the patient says that. So let me give you 2 examples here, because I wanted to say. Somebody might say that, I hate traveling by air. Now, hate is a trigger word in the sense. But immediately they'll ask the question, why do you hate air travel? Right? So basically you're saying that you know nothing about. If, let's say, somebody is coming from Sangam area here, and the person says that, oh, it took so long to come. Why did it take you so long? Oh, there was traffic. Why was there traffic? Is it unusual to have a traffic, right? So they assume the pose of knowing nothing. The advantage of doing that is you don't need intelligence. Really, you don't need intelligence because you're claiming to know nothing. You're asking questions, gathering information. And that's how a lot of earlier chatbots which claim to have passed Turing test, and they did. Because if you think about it, the Turing test was if a person is interacting with a human and a machine, if they cannot figure out who the human is, who the machine is. Now, what happens, as I said that, these kind of systems can play this game for a little while. And if the person is smart, they'll very quickly figure out that this person is just getting into a loop, because you do end up in this kind of a stage very quickly. Now, very quickly might be few minutes, maybe half an hour for someone, maybe half an hour for some very good implementation of a Rogerian psychologist, right? But eventually you will get to that point. Some of them are really good. I mean, in the sense that they know how to continue the conversation. I went for a long boat ride. Now, I didn't know what to ask for. I said, okay, tell me more about boats. What kind of boat was it? I mean, there are very good implementations which can keep someone communicating for hours. Now, keep in mind, these are systems for people who are either fighting with something. That something could be loneliness, or something could be a mental situation. These people may be okay with very limited vocabulary, with actually getting an opportunity to speak for hours might work, right? So again, I'm trying to explain here is that what is Rogerian psychologist is, but you can definitely try to build chatbots depending on your use case, and these bots using this methodology will work. Okay, so we saw two ways of implementing chatbots. One using something called a tree structure, one using a technique called assuming a persona of a Rogerian psychologist and then playing the prompt back to the user and drawing them into longer and longer conversation. Apply some heuristics, as I mentioned, a few trigger words. If you don't find a triggered word, ask what it is, like, okay, what do you mean by boat? Tell me more about boat. Or just simply playing it back to the users, hoping that they will give you more information. What else can you think of building a chatbot? What were the two types I mentioned earlier? So these two were based on this kind of structure, like question or playing it back, having some predefined thing. The other one I said is that you have a corpus-based approach, which basically means that you start with some known information, data, or knowledge, right? How do you build a conversational agent or a chatbot using some data that's available to you? So think of it this way. You are trying to interact with a help desk. A help desk, let's say you bought a new computer, or somebody bought a new computer, or let's say a music system. And you're trying to set up the music system and you're running into a problem, and there's a help number, and you call the help number. Now, that help number cannot play this game, because you're saying that don't ask me the questions because I have a problem I want to solve. So all of these help desk kind of systems start with some already known problems and answers to them, and things like what they have seen, commonly known as FAQs, right? Frequently asked questions. So if you are trying to build a system which is slightly more intelligent than these kind of bots, you start with some information or some knowledge. The question is that how do you use this to have a better experience for your user? What do you think might be the way to do it? Any idea? Just guess. I mean, come on, we have been talking about a lot of these things from the last 8 days. If you were to build a system, a chatbot, which is supposed to answer questions for pick whatever, maybe a wall clock, a projector system. It's already failed 3 times, right? So suppose you have to ask someone, you call the help desk, a computer or a modem, for example. I mean, usual thing people find issues with. How would you go about doing it? Come on, something. If I'm running a business, the first thing I'll say that, okay, I'll send a technician home. It'll cost you 500 rupees for someone to show up. They will either fix it or tell you what the problem is and you have to pay more, right? That's one model. A lot of places you call, they don't have any system, but you're simply saying that, Bhaiya kisi ko bhejo, send someone to get it up and running, right? That's one way of it. But if you're trying to automate that process, so there are 2 different ways. The traditional way, response by retrieval, I mentioned this. You create a database and somehow search through this database and then say how exactly you could solve this problem, right? How many of you have worked on a Unix operating system? Any idea? Sorry, Linux? Yeah, which is fine. How many of you? Can you raise hands? Not many? Oh, okay. The reason I'm asking for this is, so in my earlier days, I think it must be 1990, I believe, actually, or maybe 89. So I created this kind of a conversational agent. So Unix or Linux, for those you do not know, works on a lot of these commands, like ls, like wc, like grep. And what you can do, and then an interface to talk to Linux is called shell. There are multiple kind of shell, but original shell was called just shell. And then you can use these commands in a scripting language. Okay? There is also something called man, which basically has a manual entry, right? So manual entry is like your database. Then you have some of these commands. These commands can be combined together to write a script. Okay? So the problem at that time was, and I'm actually surprised that not many of you have seen Unix here. Unix was just coming up, 88, 89. And it was coming up on the mini computers or microprocessors or microcomputers as well. Not many people, even though they were in computers, were aware of Unix for 2 reasons. PCs were not very popular, so they were not even aware of the DOS. But if they had a DOS, they had a more like a graphical interface. The Unix did not have a graphical interface. It was a command line prompt. If any of you have seen, it was a prompt like this. Right? And you had a command like pwd, which says print working directory, cds to change directory, etc., etc. There were like a couple of hundred different commands, and each command was a standalone program which can be combined in a script form. So very early, as I said, that probably 89, 2 years in my job, I said, okay, I'm going to make it slightly better for the people who do not know Unix, for example. Now, so what I could have done this, which is really the hard coded way, or because I already had this corpus of information, which is the manual pages or man. So what I thought is that, can I use that and then basically add something more? If you want to add more than to what is already provided by Unix as manual, so I said that manual pages were also in some directory, and as you said, you have your own directory, and each file there can be answer to another question. So basically, these files become your corpus or part of the data that you have. Now what happens is, let someone ask the question, and I follow the same way, trigger word. I pick up the trigger word, but rather than playing it back, I would grep for that word in either the manual space, which is the provided by Unix itself, or your personal let's call it personal manual. So grep is, okay, let me define the grep. How many of you have used or know what the grep functionality is? So grep basically does, if you say grep, let's say AI in my current directory. So the grep is a utility or a command which will search for whatever is provided here in every file in this directory. So think what is happening. I find a trigger word, I search for a file which contains that word, show you the content of those files saying that this is what you were looking for. So somewhat easy, very rudimentary, almost 35 years ago, some kind of a conversational system, right? Unix manuals were like thousands of pages. You're not looking for it, trying to find out. It was easy if you can search in the index, but if you're just looking for something which is not an index, it was very difficult. You got to read through all of it. So this system worked pretty powerful because it was doing the search part, which was being done here. It was conversational. You ask a question and I search through it and then tell you that here are 2 pages or 2 files that you should go through. Was it answering the question 100%? No. It was helping in locating that information. That's response by retrieval. So what's going on is it's trying to get the context, which is a trigger word, which is what I was doing there earlier. Searching that information, grab a response, and the command in Unix is called grep. Doesn't matter. You don't need to do this. You can do more fancy things. When I say more fancy things, it would be something like you may have a proper database. You may write SQL queries. You may write NoSQL database and make even more interesting or more complex queries. You may use fuzzy logic, which means that it's not just that word, because the grep is actually searching for exact word. How many of you are familiar with regular expression? Has anyone heard the term called regular expression? Regex, yeah. Come on, anyone who's doing data science should know regular expression. Right. So regular expression lets you define. So let's say I am saying hotel. So I'm not sure should I have H lowercase or H uppercase. So instead of saying that, making 2 searches, I can say that one word, lower or uppercase, with this, right? And this is in the beginning. Or you could say in the beginning H and anything after that. So regular expression is a way of specifying in a fuzzy way what you are looking for. And then there are regular expression evaluators which will actually match with whatever is in there. Regular expression is a very powerful thing. If any of you, and I thought somehow some of you mentioned you are interested in data science. If you are in data science, the regular expressions are a very, very powerful tool that you should be aware of or probably make use of it. Anyway, so that's the response by retrieval, which is how a lot of chatbots were operating in the, let's call it, second generation of conversational agents. How about the next one here? Response by generation. The moment you see the term generation, that sounds like generative AI maybe, right? So what is going on is that modern corpse-based chatbots are data intensive. You might be looking at the case laws, you might be looking at the legal cases, you might be looking at the medical history cases, right? They are requiring to search through thousands, millions, billions of words. So this kind of rudimentary thing where I was supporting about 200 odd pages here, maybe a few hundred more of your personal written thing, is nothing in front of like when you're searching millions and billions of words. There you could obviously do response by retrieval, it will work. But if you want to use the or utilize or get benefited out of the all the new things that have happened in the area of neural networks, you may want to use the response by generation. So now apply what we learned in the last 8 days, and can someone tell me how exactly will this work? You have a lot of information that's available to you, millions or billions of words, which is really the data that you are or you can rely on. But rather than doing response by retrieval, you want to do the response by generation, means use the, let's say, neural network or generative AI to help you here. Come on, any idea? You need to play Tombola, the one who has not crossed any square yet. So if you haven't spoken so far in the last 8 days, you should speak up now, right? See what we are doing. I mean, if you're doing response by retrieval, you're trying to search through whatever information is available to you. If you're doing it by generation, what did we do in generation? We said it yesterday, right? If you're trying to build the AI system, what do you do first? What's the first step? Rather than building the database, you actually train. You train the model. You train the model in whatever information is available to you. And then predict the next word. Given some context to you, you predict the next word. And while doing that, you generate the answer. So it will look exactly the same what we have been talking about last 3-4 days. User gives you a term or a query, and whenever the user's turn is, and you have the lot of this data, let's call it C, which is a corpus of conversation. What you're trying to do is to find out an R, a next term or a sentence, which is very similar to Q. That's what you're doing. Here I use the grep command to do it. Now you are saying that I don't know. I learned everything that was in here. When I say learn, it has been converted into a high dimensional vector space. I form the vector of the user's question or user's query, and then say, can I use that to find the most similar thing in my database? Right? One other thing I mentioned earlier, in the sense that you're doing a vector dot product to find out similarity, right? That's what we were doing earlier in the attention mechanism, which we were talking 2 days ago. So exactly the same thing is happening here. The only thing I added here is that I mentioned that what exactly is going on there. It's called TF-IDF cosine. You can search for it, especially those of you who have interest in it. It's called term frequency and inverse document frequency. Very similar to how the Google search functions. Does anyone know how Google search functions? So 2 things. First of all, the Google search is not using generative AI. It is still doing the first method which I mentioned, which was the response by retrieval. What it is doing, but it is employing something very similar to TF-IDF cosine calculation. It's not doing the calculation at the runtime. Basically, what it is doing is, okay, a computer science question. How many of you are familiar with indices or trees? Okay, which one? What do you know? B tree? You're familiar with that? Okay. How about the inverse list? Have you ever heard of inverse list? No, not inverse. The index which is in the reverse indexing. Any idea? Okay. All right. I'm not familiar with B tree. B tree, anyone know? Okay, let's not go there then that far. Basically, what is going on here is, let's say you are using Google search. Google has, let's say, I'm taking a very simple example, only access to 100 documents. let's say it's a day one when the Google search was invented, right? What is Google search doing? It's basically reading through all these documents, converting them into words, and then trying to figure out what words exist in these documents, and then it creates an inverse list. For each word, what is the frequency of that word being used, and which documents are having that word? That's the list it is maintaining. When you're doing a search, it's basically finding out in this list where that word is, and then basically going to the index which tells us which 4 documents have this word in there. It also has frequency. So it will show you the word which has the, let's say, maximum number of occurrence of that word. It will put that at the top. And I'm saying a very simplistic implementation of the Google search. Then it created more ways to figure out which one of these 4 is more relevant, because it didn't have only 100 documents, it had 100 billion documents. The search queries are not returning 4, but 400,000 results. Now, how does it figure out which one is more valuable than the other? There are other ways of doing it, but let's not go there. Let's say it has these 4. How does it find out which one is more relevant to your interest? It uses a vector space calculation called cosine similarity. Cosine similarity goes by saying that more the frequency of the term being used and inverse document frequency, less number of document on that word, or less number of documents containing that word, higher the likelihood that it is more relevant to you. Does that make sense? Right? If you have 100 documents available to you, only 2 have the words that you are looking for, and one of which has that word 5 times as against the other one only 1 time. There is a likelihood that the one document containing 5 occurrences of this word is more meaningful for you. Right? Let's say you were using 2 words to search, W1, W2. W1 returns that there are 40 documents that has this word. W2 has only 4. Think of it IDF, which is the inverse document frequency. What Google determines, or what this particular cosine similarity principle says, that the word which has lot of occurrence in terms of the frequency of document is probably less relevant because there are too many of them. The one which has less is more relevant, so it's going to give higher weightage to this. Now, how does it calculate that? So that's basically is the cosine similarity, and next slide will explain a little bit more detail. But eventually, what you're doing is this. You've seen this earlier, right? This is a neural network calculation. It figures out the TF IDF cosine, which is very similar to attention mechanism we talked about, and it calculates the probability, which is doing a cosine calculation of which of these 4 documents should be most probable for you to look at. That's a cosine similarity. It's a dot product, magnitude of vector. At the end of the day, points to remember, it will give you -1 to 1. -1 tells you that the document is irrelevant. 1 tells you that's the one you should be look at it. Still not neural network, right? But very close to that. What it is doing is that it's relying on something called a cosine similarity. That is nothing but a dot product calculation or of a vector product or matrix multiplication that can be used to figure out which one is the most relevant document for your search query. Now, I gave you half the answer. What if you need to convert this to a neural network? What's going to happen here? Come on, guess. How are you going to do whatever else you want to do, healthcare, remote sensing, building a model, I mean, all big things, right? If you can't think of a common, simple problem, which, by the way, was already solved without using neural networks. What are we going to do? So, instead of assuming the similarity equation, we're going to use probabilities, right? That's what the neural network is all about, computing probabilities. So what we're going to do, if you look at this one, an argmax function which is actually calculating the possibilities by figuring out the similarity, we're going to replace this with a BERT dot product, which is very similar. I gave you a hint that the attention mechanism is what you're doing, right? So instead of doing the cosine similarity calculation, you let it go through. So two changes are happening. One is that this corpse is not using this reverse list which Google was preparing. Instead of this, it is being used for training the network, and then you're using an encoder-decoder mechanism like BERT, which is basically performing exact same thing for generation. Rather than searching, you are letting the neural network compute potential solution, and you assign them probability, and then those probability will tell you which one is the more probable answer to your question. Does that make sense? Do you think it will work, or it can work? Who thinks that it's a potentially good solution? Or the other way around, who thinks it is not a good solution? Come on. Something. Today is the least interactive session so far. Listen, there's no right or wrong answer, right? So give me your opinion. What do you think? Will it work or will it not work?
I think it will work.
It will work? Okay. Do you see many of these chatbots being built that way? Why?
I'm not aware of that.
Okay. So actually, let me put it this way. So the three things I asked here. Clearly it will work, right? Because the language models are doing a lot of things. It is generating its creation of the new content, so it will work. Now, the moment you say it will work, there are a couple of different issues. There's an issue that we talked about yesterday, hallucination, for example. In any generation, you do not know if it gives you the wrong answer. I gave you the example where Air Canada was fined by the courts because its chatbot was giving all wrong answers. Even though the answers were there, but it was assigning probability, picking up the wrong answers, right? Third thing, also we talked about yesterday, the cost involved in actually writing a chatbot using neural network is way more higher than doing it the way the Google search is happening right now. So yes, it will work. On two, it will work, but it will have a potential whole lot of risks. Do the risks outweigh the benefits, or the benefits outweigh the risk? The jury is still out. It does answer questions very well. Actually, one of the startups that I work with, we use an LLM-based chatbot to answer a question about the product. 9 out of 10 times it does very well, in the sense that it answers the questions which it does not find in the training data explicitly mentioned. So it does show the latent space and the finding relationship together. 1 out of 10 times it gives the wrong answer. Now, there are guardrails that we have built up in the sense that rather than giving a wrong answer, except that I do not know this, or say that contact the help desk at this number or at this email, or whatever the case may be. Right? Okay. So let's say that it's doable, it's expensive, it may be a little bit riskier, but potentially a good way of doing things. Are these chatbots a good way of interfacing with neural networks? Yes, no, maybe. And that you should actually have some form of opinion. If you have used ChatGPT, you have interacted it as a chatbot. It works as a chatbot, right? So what are the pros and cons, basically? I have had here a slightly different interpretation, not a ChatGPT in general, but its utilization by either an organization, a company, or maybe a court, maybe a medical system, maybe a legal profession, maybe a tax consultant. I mean, those are some of the use cases. Most of the same problems. I mean, it's fun, it's good for narrow scriptable applications, but the cons is they don't really understand unless you have a huge corpus of information where they start trying to get a feeling that we saw with neural network, where it figured out that the relationship between king and queen is same as men and women, for example, right? Or it figured out is the relationship between India and Delhi is exactly same as in USA and Washington, D.C. No one told it, but it figured it out, right? Expensive, brittle, sometimes they can mirror training data exactly, garbage in, garbage out. Again, all the problems we talked about yesterday, because if you have a chatbot which is becoming an interface for your organization, and if someone who want to sabotage your implementation or want to hurt your branding can train your chatbot to do things that you won't want it to do, right? I mean, if some of you who are doing branding or marketing or those kind of things, right? A lot of brands do not want their brands to be associated with some other things. That could be some other thing, could be a celebrity. If they have in a negative news, those brands don't want their product to be associated with them. So a lot goes in making sure that your branding is working as per your plan. If you leave it to a neural network driven system, somebody else can sabotage, right? All the risks that we talked about yesterday. Okay. So far so good? Okay, let's do a quick look into the implementation of a frame-based system, which was a goal-driven tasks. I'm not going to take too long on this, so I'm going to quickly move on to the second topic that we want to talk about. So generally what you're doing here, this architecture will look like that you have a structure, call it data structure, information structure, which is trying to capture user intention. The user intention is driven by whatever the goal is. So for example, this is what our goal was, this is what the capture of the intention will look like. How do you capture the intention? One of the earliest implementation was done in 1977, which is what I've used it here as an example. I think the reference is there somewhere. What you're trying to do here is that you have set of slots which require to capture user's intention. There's a domain ontology, which is basically saying which words you want user to say for you to recognize, and you're trying to capture those. Slightly different answer, slightly different example here, frame-based dialogue architecture. There's a chatbot which is trying to get user intention and fill that structure that you saw earlier, right? This is just an example. It may ask questions, it may clarify, it may confirm that there is no illogical or invalid answers. There could be some validation associated with the responses that you are providing. Is this model better than the first one? What would you prefer? Let's say you're working for a bank. You're trying to create a conversational agent that, let's say, I don't know whether we do demand draft today or not, but assuming we do demand draft today, let's say it basically wants to have a system that lets you request a demand draft be sent. Or maybe let's say simple, make a bill payment. Let's say you got the electricity bill and you are trying to instruct your bank chatbot to pay the bill, right? Which method is better? This one, frame-based dialogue architecture, or the other one, which were the retrieval-based or generation-based architecture? Which one is better? They could be highly precise because it's a very clearly defined goal. It's a clearly defined requirements, what needs to be there to have that goal. They may also have validation, as I mentioned, when you are providing the answer or gathering the user's intent. The negatives are they can be expensive and slow to create rules because they are very similar to rule-based system or expert system. Somebody needs to define the rule. If the rules change, if the laws change, if the rates change, you need to have a high maintenance there. But they would be more successful, more predictive, less error, less confusing for the users. So, what did we say here? Can someone summarize or have a question before we move on to the next area? Anyone? No questions? Okay. So let me just do a quick 30-second summarization and then see. Keep in mind, you have to learn something to use it in a situation that I have not mentioned here. So what did we do? We looked at the chatbots or conversational agent as one type of application where generative AI might work. And very similar to what we did like in last few days, we looked at historically how exactly they evolved. So they evolved from a Rogerian psychologist-based implementation of asking questions, and we saw a limitation of that. Then we saw that a call tree kind of an implementation where you're asked to provide or pick one out of many choices, and then you follow that. Either you get a success or you end up at a node called frustration because it didn't do what you expected it to do. Then we said that the second type of implementation would be a corpse-based implementation. You could actually organize it in some form of database, or you could do it like the Google is doing. What Google is doing is implementing some kind of similarity algorithm to find out which document has higher probability that you are interested in that as against the other ones. This is, you can implement it as a SQL database, NoSQL database, you are querying, you're searching, you're getting the results back. And finally, we said that you can actually also use the generative AI-driven conversational agents. You're replacing database with learning, and you're replacing the cosine similarity with some kind of a self-attention mechanism or the BERT dot product, and then trying to do an encoder-decoder structure, and then get the answer. Then we said that, will it work? The answer was yes, it will work, but it has limitations. It is expensive. People, your opponent can use it to train in ways that you don't want your brand to be acting or doing things. Then we differentiated between a goal-based conversational agent and a generic conversation agent. We said goal-based conversation agent may work better when you have a well-defined structure that you're looking for. If you have all that information, you can actually even validate that before acting on it. Those systems can be highly precise because you know what you're looking for, you can validate it also, etc., but they are expensive to build, expensive to maintain and change. Now, the bottom line is same. We looked at 4 different ways to implement a conversational agent. Depending on what you're trying to do, you pick one or the other, right? Or come up with the 5th one. Okay, anyone has an idea to build a startup, trying to build a conversational agent for, I don't know, counseling when a new student gets an offer or an admission offer, right? Probably a good use case, build a conversational agent. Yeah? All right. No questions? No ideas? $1 billion startup idea. Okay, all right. So let's move on to the next topic then if there are no questions. Now, I do want definitely for someone to talk about more. So all 4 of you who were doing the GIS, okay? I know what it is, but probably this height doesn't know what the GIS is. So I want one of you to actually explain before we go on to this. What is remote sensing and what is GIS? Who wants to explain? Come on, I got to give you some homework. You gave me homework to prepare this, right? So you have to explain to this side of the team, this side of the class, that what is GIS and what is remote sensing.
Remote sensing is basically sensing features on Earth using some remotely. So using sensors, which for example satellite sensors, you can capture a photograph and use it as digital
Right, this side. Do you understand what is remote sensing imagery is? Okay, so great, thank you. I mean, that was a good introduction. So what we are doing, we're switching gear and trying to look for a new type of application. The one I chose earlier, conversational agent, was something which I presume majority of you were familiar with, had interacted with it, and probably had opinion also about it. Now this is interesting area because it's very specialized. It's pretty close to at least 30-40 years ago when I was working in this area was like a very esoteric area for two reasons. Okay, before I go to those two reasons, what it is. In a way, it's a photograph. When you take a photograph from your camera, you're actually taking some area. It could be 1%, it could be 10%, it could be, if you're using a zoom lens, you're probably taking an image which is 100 meters away. If you have a more powerful lens, you can probably be shooting 200 meters or 300 meters of imagery. Now, farther you go, more information in your picture. You take a close view of a person, you only see one person, two people, or this class. You move farther. If you remember on day one, we all took pictures. We were like 50 of us, 60 of us. The person kept moving back because everybody needed to fit into the screen. Do these pictures or images interesting? Are they interesting for you? I guess the answer is yes, right? All of you, if you take out your phone, will probably have 5,000 photos on it for multiple reasons, right? So that's your photos and images and cameras, right? Then what happened is that when we started sending satellites in orbits, right? You know all what the satellites are. Yeah? Yes, no, maybe? Has anyone seen a satellite? No? Anyone here? Which one? Where? Go on. You saw the models, not the real one. All of you have seen satellite. You see it every day. Yeah. Moon is a satellite of sun. Right? So what is a satellite? A satellite basically says that it draws its energy from another source. You can see the moon because the sun's light reflects on it. Okay. Now the moon is one satellite. The earth has its own satellites that we send out. Right? What's the difference between moon and the satellites that America has sent or India has sent?
Moon is a natural satellite.
Uh-huh.
And others are man-made.
Okay, that's one difference. There's one more huge difference actually. The man-made satellites that we are sending are called geostationary. Does anyone know what is geostationary and why they are called geostationary?
They seem stationary to Earth because they are
Correct.
the exact.
Correct. The earth is rotating on its axis, earth is rotating around the sun. Geostationary satellites that we send, they are going in the near earth orbit. They're not as far as moon. They're actually a fraction of distance from the actual distance of the moon, but they are placed at an orbit where they look at the same space continuously. So with respect to earth, they seem stationary. They're not. They're moving. Earth is moving, they're moving, but they are stationary relative to each other. Right? So, what do these satellites do? What do these satellites do? Do you use them? Right. Your mobile phones use GPS. The GPS is a functionality provided by these satellites. More than that, initially the satellites were used for communication, telecommunication. If anybody has electronics, you do antenna design, you do communication, right? So they were initially used for communication. That was the first intended use. Then researchers realized, once the camera technology improved, the lenses improved, that if they are looking at the same spot continuously, can we put camera on there? the camera technology has improved big time, but now there are satellites which are not necessarily just the communication satellites, they are remote sensing satellite. Now what is remote sensing? A very powerful camera looking up from, let's say, 200 kilometers high or 50 kilometers high, capturing photographs of the Earth and sending it back to us. There's a whole lot of improvement in 30 years when I was working in it. Cameras have become powerful, communication has improved. There were a lot of problems. Earlier camera was very, very poor in terms of resolution, in terms of its power. You know how the cameras work, right? Higher the power, better the pictures you will get, better resolution you will get. Then the problem was that, yes, you've got a lot of data. You got like 10 gig of data. How do you send it? It was not easy to send the information down. You can take a picture, but it takes 2 hours to download. It used to take days to download the data, right? All of these improvements have become now possible. You may have seen newspaper reports where they show movement of enemy forces, the constructions being done, comparison images. This is how Allahabad looks like before Kumbh, this is during Kumbh, this is after Kumbh. You might see those kind of images from the sky, right? You may have seen the pictures of which city is lit up. You go closer to Delhi or Mumbai, and then basically you see that there's a lot more lights out there. So, point I'm trying to make is that remote sensing imagery is just like a photo. It's a photo at higher resolution and higher dimension. Any remote sensing image actually covering some physical space on Earth, right? Now, fast forward today, let's say now you have access to a lot of these imageries. Each of these images has a lot of data. Now you have a problem of interpreting these images, right? Which is a problem what you solved for Facebook when you basically identified your friends. What were you doing? You were identifying a feature. That feature, by the way, happened to be your friend. But when you are interpreting a remote sensing imagery, you're trying to identify, is it a building? Is it a farm? Is it a wheat farm? Is it a sugarcane farm? There are multiple reasons to do that, actually. Let's not go into why we are doing it. But the issue is same. Facebook wanted you to identify who this person is, right? Remote sensing application, I don't know what they call nowadays, but people who are trying to interpret imagery are trying to identify a feature. Is it a road? Is it a river? Is it a ditch? Is it a mountain? Is it a building? Is it a hospital? Whatever the case may be, right? There are a lot of use cases. I mean, I can give you a few of those things basically. Remote sensing imagery was being used in 1988 to make a better estimation of how much wheat is going to be produced, how much rice is going to be produced. We can go into politics and all kinds of things as that people were estimating or not estimating. How many people are, one of the early use cases that we had was that to calculate the amount of deforestation in national parks, right? I mean, if you go by land, visiting them, you make one estimate, but if I'm getting an imagery of a year ago and today, I can visually see them. I can actually extract the features of where the forest cover is still there versus not there, and I can estimate that, okay, we have lost 7% of the forest cover over a period of time. A lot of applications. I mean, I guess today the applications may have changed, but all kinds of things that we were doing, right? As a matter of fact, one interesting project that I was involved with was very, very, I would say, I actually don't know how successful it was. Are there any people who eat fish here or engage with fishery? Fishing is a huge exercise, right? It's part of agriculture. The fish is raised as agriculture. People who are involved in fishing, not the fishing in the river, but in the sea, deep sea fishing. It's a massive operation. There are big ships involved. They actually have massive nets also. If you think about it, the fish in sea especially don't stay in one place. They move. So if you're running a big deep sea fishing business and you go at the wrong place to do fishing one day, you may not find any fish because the fishes are moving. So one of the experiments that we did was, can we use remote sensing imagery to help the deep sea fishermen to locate where the fish are on a given day? And if somebody is interested, we can talk about it later, but I'm just giving you an example of the imagery. Now let's see. Let me ask the people who are doing PhD there, where do you see the use of generative AI in remote sensing imagery? And the reason I'm saying that I want to understand your perspective, I have just one example that I included today here, but there might be many more.
I'm not sure, but maybe to produce data where similar data where the data loss is there in the image. For example, clouds, they disrupt the information capture. So we have blocks where the information is not captured. Maybe there, similar to the neighborhood pixels, maybe we can generate better user.
Okay. All right, let me try to rephrase, and we want to stop in about 15-20 minutes for the break, and then we'll continue a little later. So very similar. The use case that I picked up is very similar. Now, I'll mention one more thing before we go here. The area which is being helped in remote sensing imagery interpretation is very similar to what you would normally do in image processing. If anybody has done a subject of image processing or a course in image processing, you would know that, right? All kinds of mathematics obviously there, a lot of filters, a lot of feature enhancements, feature identification, right? So one of the use case that we can think about, and that's the one I'm taking the example of, again, a published work, not my work, obviously. So you can actually look into this. Maybe you guys are familiar with it, those who are doing a research on it. Think of a situation where you have access to these remote sensing imagery, very similar to what Facebook was doing 10 years ago, trying to identify your friends in a photograph. Here you're trying to identify MNNIT guest house from a remote sensing imagery. Can you do that, right? So if you're trying to follow the Gen AI, right, go back to what I talked about on day 2 and day 3. You're building an AI-based system. What are the steps? The very first thing that you need is to train the system that you want to do. To train the system, supervised learning, you need to have data where you can train it to say that this is what a building looks like. This is what a housing complex looks like. This is what, whatever, a train line looks like. This is how a road looks like, etc., etc. One of the problem that is being looked at, it was always there. I mean, it was a manual exercise. It was an exercise earlier trying to use the image processing techniques to make the image look better. There are all kinds of mathematics involved because really speaking, these images are not two-dimensional. There's a parallax. There's really an overlap of images. You want to sometimes join these images. I'm leaving out all of that thing. So let's say you're trying to build a generative AI which can help you interpret an image, a remote sensing image. The first step, you need to train it. Can you use Gen AI to generate the synthetic training data? Because unless you can train, the Gen AI cannot help you with interpretation. Make sense? So let's look at it. If we are trying to build a system that can help us generate data for training a large language model. So a little bit of a circle here. We are using the large language model to generate the training data, which will be used to train another large language model to actually use the real remote sensing imagery and predict or identify or extract features from it. Make sense? All right, let's look at a few of these things. So a typical sample is going to look like these are black and white images. These are images which look really bad, and you're trying to identify what is in this image. A typical remote sensing expert would be looking at these images, trying to make sense of it, trying to get the meaningful, actionable intelligence out of those things, right? So our goal here is to say, can we use these artificial sample and train so that it can be used to identify natural geographic phenomena or even man-made structures for that matter, right? That's the goal. Does it sound familiar or something similar? So what we are trying to do is something like this. You may start with this kind of image or this kind of image, and then you can try to identify what's in there. It may be a a bridge, a forest, a stadium, an industrial complex, parking lot, shopping center, whatever the case may be. Basically, you're doing exactly same thing as I mentioned earlier already twice, that you are identifying your friend and putting a label on it. You're identifying a feature here and assigning it a label, right? As simple as that, right? How would you go about doing it? I mean, I'm asking this question, but the answer should be very familiar by now, because it doesn't matter what problem you're trying to solve using AI, all or most of the solutions look very similar. Supervised learning, training data, build a mechanism to do unsupervised, and then search, which includes generating labels and assign probability, pick one. I mean, there are a lot of details behind it, but in general, it'll look like exactly same, right? So, if you think about it, what is it going to do? It's a classic machine learning problem if you think about it, because you're giving it data, you're assigning labels as your supervised learning, and then giving it more data to say, can you use your learning to identify this? But it's not trivial, because it's not trivial for words and sentences. It's even more non-trivial for something like an image, which is not very clear. So, a lot of things where the samples could be imbalanced. Now, this is again a very similar thing in what we talked about, the TF-IDF similarity. Think of it this way. The feature that you are most interested in is the feature is most rare. Because if the feature is everywhere, then you're not interested in it. If I am, let's say, the Defense Ministry of India, I'm interested in finding out where is the nuclear power plant for whatever country I'm, let's say, interested in. I'm not interested in where the houses are or where the shopping centers are. I'm interested in where the other strategically, militarily related point, right? So the thing that you are most interested in is the thing hardest to find. If it is hardest to find, how do you even train your network? Because if you can't even find it, you can't use the label for it. Now one might say that, okay, just train it with any other label. That defeats the purpose, because it will then find the right things and say that this is what you're looking for. So one of the ways you can do is use the synthetic data. Use the generative AI to generate the data that is very similar to the real rare occurrence of a feature that you are interested in, and use that for learning. So same way what I'm saying is that frequently occurring classes is not an issue, because that can easily be done. All neural networks are greedy. Remember, I've used this term greedy a lot of time. You are trying to figure out the best thing to do for a rarely occurring object, because that's the goal. Okay? Specific example, finding it complicated, and very few such objects exist, so we have a problem there. What are we going to do? Okay, so two things here I'm going to do. This is a problem which is normally used by, have you guys used, or any of you who are doing the PhD in remote sensing or GIS, any sample databases for images that you have used to train whatever? Yes? No? Which one? Which one? Okay, all right. So I was a little afraid that if I'm going to give you an example that you're already familiar with, you're not getting anything new. So this is the research which was published, I think, last year. Okay, I don't have the year here. So it's using another publicly available data set. So obviously I'm giving you a new example so you can start using it and try to figure it out. So it's using that database. So here's an example from this. It is called AID, a benchmark data set for aerial scene classification. Have you seen this one? Okay, have a look at it. So what it has is that I think thousands of images, I don't know the exact number, a couple of thousand images where each of these things are defined. What a forest looks like, what a baseball field looks like, what a beach looks like, all kinds of, what a railway station looks like, because you're going to use these images to train your model and then give it an image which is unlabeled and then say, can it identify features, right? The question is that how do you go about it? The basic solution is exactly same, right? You get the data, you label it, have the learning process run as a supervised learning, make sure that your model learns the right thing, and then start experimenting by giving it unseen pictures. There's one more thing we talked about. Don't use all your training data for training. Don't use all your training data for learning. You keep it for validation also. Remember the step I used called regularization. You don't want your model to learn exact thing. You want them to generalize. So that if you've seen one beach, you should be able to identify a beach which looks same but not exactly same, similar. Right? You want model to generalize. Everything that we talked about day 4, 5, 6, etc., they're all same things, right? So what this is doing actually, this work, it's using these benchmark data set and a process called diffusion. Have you heard of diffusion? Denoising or creating more crisper data sets. Now that is also, the advantage there is that there's a library which actually is available in public domain that you can use. So you can use this benchmark data set, you can use the library to generate more imagery to train your model if you wish to. So what it is doing is that diffusion model training on all available classes. Classes means the class of imagery that is showing you to learn one type of feature, and then use it to generate more data, right? Now keep in mind, I mentioned that synthetic data is a problem because synthetic data may actually reduce the learning, but in the cases like this when we do not have the data, this is one way of doing it. Can someone remember an example? I think 2 days ago we talked about where the same kind of approach, was it? Yeah, day before yesterday when we were looking at benefits. Come on. If you're looking for a job in Gen AI, how are you going to do it? There was specifically an example very similar to this. Healthcare, brain imagery, for example, or any kind of data. You need synthetic data to train your Gen AI or your model so that it can be used for the other purposes, but we don't have that many of scans, right? It's a health data, it's a public, it's a private data, it's a secrecy issue involved. So you need to generate those kind of samples to actually train them, okay? So right now I'll show you an example of what was produced. This was a training data for identifying mountains. So this was generated applying diffusion model. So the goal here, what I'm describing here is that not to use the Gen AI for actually feature identification, but use a specific model to generate more synthetic data to train the Gen AI. The way it works is actually you're finding out noise in images. So you start with an image, find out the noise, filter the noise out, build the feature that you're interested in more sharp, more easily identifiable. Okay? The way you do it is that you run the same process over and over again, create distortions, and then use it to have some kind of a GAN, which basically tells you, is it desirable, is it not desirable, have a feedback mechanism, which basically says that, is the noise helping you get better image, or it's getting more of a distortion than in the wrong direction. So really what you're doing is that you're introducing the noise and hoping to get that noise which is to generate a clear or a clean image. Have you ever seen an example where a service comes along and says, do you have a picture or a photograph of your grandparents, for example? A fuzzy black and white picture that may have lost colors, that may have lost even the shades of blacks. Right? There are services which are actually taking that picture and cleaning it up and give you a colored view of your grandparents or like some very old picture, right? All of it is happening based on very similar technology, right? So what we are doing is that we are saying that we are introducing noise not to obfuscate but actually enhance the image so that it can help us do the feature generation. So let me show you an example how this specific model worked. So you started with a dense imagery like this, which is actually an area which has a lot of housing. You run the multiple iteration of this particular diffusion probabilistic model, and there's a reference for the paper that I'm describing, and that's where all the imageries come from, and then iteratively get to the point where these features becoming more and more better. Now, this is not a typical image processing or a remote sensing mechanism thing, because the idea in the remote sensing was to go the other way, remove noise, which is what you would do if you are manually working on it, in the sense that if you are really working on one image and trying to get better. What we are trying to do is the other way around. We are introducing noise, but the goal is to not obfuscate a feature, but iteratively make it better so that it does look like what we were looking for. And then use that synthetic data to train the model, which can then be used to identify features of interest. Make sense? Yes. Okay, so that's a good question. Anyone can answer? Do you have an idea? How does introducing the noise help?
So in diffusion models, the noise is being added, and the model tries to reduce the noise again to get the original image. It is a way to train a model in a better way to get the original data or the extracted data.
Or better data, yes. So the noise is a known term that's being used. I could have used a perturbation as a term as well. So the noise is just being, so think of it this way. You have a fuzzy data. That is not the exact data that you're looking for, right? One way to say that, I know what modification or perturbation I need to do to get to the real data. If you know that, you can do it. Lot of existing image processing or remote sensing image processing goes on that logic, that I will remove this, I will make this change here. Here, you don't know which is the right way. You are introducing a perturbation. Same thing like a feedback, and then you figure out, did it make it better? Did it make it worse? If it make it worse, go in the opposite direction. So you are introducing the noise in order to get better outcome. That's what you're doing, which is what a diffusion model usually does. Okay, anybody else or any questions? This is not just limited to the diffusion model, and not just limited for image processing. If anybody is in financial domain, the stock price movement is based on diffusion model. Brownian motion, I don't know if anybody has heard of it. I asked this question earlier also. Not Brownian motion, but the pricing of a derivative, which is also based on diffusion model actually. I mean, if you think about it, almost every phenomena in the world is probably using a very few basic fundamental mathematical techniques, or you can model the real world using those basic mathematical techniques. Okay, one last opportunity. One more question before we take the break, if there is any. Yes, no, maybe? No. Okay. All right. So why don't we take a break here, and let's meet at 20 minutes, 11:50, right? And when we come back, we're going to talk about the last topic for the day. If you're trying to build a language model, how exactly you're going to go about it. Okay? All right, guys. Let's just take a break here then. Okay, so who remembers that? How do we go about building an AI system? What are the steps generally that we talked about earlier? Right? What are the steps?
I think organizing the data, then going for the algorithms, building neural networks.
Okay, all right. So let's try to rewrite in what we are saying here, right? So what is our goal? Our goal is to build an AI system. Where is that here? Okay, so we're building an AI system. So very first thing that we need is to make sure that there's going to be a learning somehow. So that learning requires two things: data and a process by which the learning needs to happen. That could be supervised or unsupervised. As part of the learning, you say, how does that learning happen? So I'm making some assumptions here that we're going to use the neural networks. Let's say deep neural networks, but neural networks. And then we need a way to calculate the probabilities, because that's what we are going to do in terms of what's the final output is going to be. And how is that relevant? Because we are trying to find out, are we looking for a binary answer, like a classification, like a sentiment, or we are trying to get more of a probabilistic distribution, which means that we are going to use some kind of a softmax because we are trying to find the relative probabilities of the output, right? So that's roughly what we are going to do. And then I also said that learning is not just learning the weights and biases, but how the neural network is designed, right? That's what we're trying to do. Even before we do all this, right? One of the things I had mentioned that training these neural network or building these models is not an inexpensive process. These are all expensive phenomena. There's got to be a reason why do you want to build the model. So very first thing that we want to do in this process is to make sure that you got to figure out what is the use case for the model that you're trying to build. I've used the term base or foundation model. Those models are available to you, right? And I also kind of taught about or discussed that how do you tune that model? How do you modify that model? We actually identify that as a risk also, that somebody with malicious intent may actually go and change the learning of the model in a way that is detrimental to you, your company, your brand, or whatever the case may be, right? So even before you go and making your own LLM, you got to figure out what's the need, what's the business case, what's the use case for building a new large language model. Why is it important? Because it will have an influence on model size. If you remember, the size of the model determines how many weights and biases it needs to calculate, how many neurons does it need, which means how much cost is involved in training and or executing the model. If you remember that, I mentioned that ChatGPT-3 was making almost 1 billion calculation for predicting each word. Do you have manpower? Do you have the cost? Larger the model, more training data is needed, because larger the model, more parameters. More parameters, more training. Now, all of these things are generic statements, because as part of learning, we also kind of found out or learned, or researchers found that sometimes dropping the output of a neuron makes the learning better. But it could be that there is one layer where you're using dropout as a regularization technique to generalize the learning of the model. But in general, Larger the model, higher the parameters, higher the cost for training, or more training data is needed. What's the computational resource? Memory, compute power, storage space, all kinds of things you need to figure out. So there's got to be a very, very important reason for you to understand why you are doing this. Right? You're trying to use the power on your computer. You might use it for some purpose, for some toy neural networks, but if you want any realistic neural network, you've got to rely on large computer center, large compute power, storage and compute, mostly the compute. You can make smaller things and let the learning run for hours. It's fine, it'll work eventually, but then again, you'll run out of limitations, run out of space and or into your limitations, right? Yes, you can use the toy systems to really learn the process, but that's okay, right? That's what we're trying to do. But if you're going any realistic development of LLM, you're definitely having to figure out what's the use case, because that's what will determine what your requirements are and should you not be building. Okay? Now let's look at the use case in the sense why you might be building. Now when I say you, it could be your company, right? Now you can go back to whatever we talked about in terms of the drawbacks, the risks, the disadvantages, and say that we may be focusing on one or more of those things, and that's why we are trying to build. So some of the reasons for building your own large language model or a language model: domain specificity, in the sense that the base or foundation model may not have information. That may not be the only reason. I mentioned this as a use case, what we are doing in one of the companies that I work with, but they're not building their own language model because it's too expensive. Nobody's going to pay for it, or we won't be able to generate enough revenue out of it to justify the investment in it. We are using the RAG, which is the retrieval augmented generation. So rather than building the model, creating the model of our own, we are actually fine-tuning the model. Obviously, prompt engineering is the first one, and then the RAG, because those are much more effective or efficient way of adding domain specificity to a base model. Obviously, you can create a model with industry-specific data. That's always a possibility. Greater data security. Now, that's a larger problem. Now, one might say that, yes, we could use a RAG or a retrieval augmented generation, but we will have to send the data to the public or a base or foundation model, wherever it comes from, OpenAI, Meta, Llama, whatever the case may be. We don't want that. So we want our own data. We want to stick with it. So we want our own proprietary model. That's another reasoning why we want to do that. Ownership and control is another one. I don't know the exact number, but there were more than 200 different implementations of the base and foundation model. Some countries build their own models, some companies build their own models. There are some open source consortium who built their own models and made them available, etc., etc. Personally, there may be one in India. I haven't yet come across that in India somebody claims that they have created a base or a foundation model yet. I'm sure somebody must be working. The government must be trying to do something. Some agencies might announce it soon. There are some other sovereign nations. I think Saudi Arabia actually has, some countries have announced their own national models as well. Let's assume that you have determined the use case, you have secured the funding, and you're not doing it just for an exercise, which is what the goal is we are describing here. You've got to decide what would be the architecture. Right? Just like a software architecture course that I teach for the entire semester, one may argue, what kind of architecture do we want? Now, we're not going into all that detail here. If you're realistically doing it, you would make that call because there are now alternate architectures available. Right? We talked about a few earlier. But for the sake of this conversation, for this section, about half hour, which is what we are already like 8-9 minutes into it, let's assume that we are not spending time on investigating multiple architectures. We did talk about earlier in the course, but let's say we'll stick to transformer architecture because that's what is the most commonly used architecture for large language model as it stands today. You can call it state of the art. I mean, fine, it's not discovered last year. It's been around for now close to 7-8 years, but it is still one of the most commonly used architecture for large language model, efficient language model. So let's say that we're going to use the transformer architecture. Why? Because it captures the underlying patterns and relationships. That's why it's very popular. We saw this example, what the latent spaces are and things like that. It handles long-range dependencies in the text, which means you can have a larger context window. If you remember what the context window was, that's the window in which the attention mechanism is working, which means that it can look back and can figure out the context, maintain the context, give you the answers and things like that. That means higher dimensional space also. So every time you go with larger the training data, larger the number of variables it needs to do, everything there. It can process input of variable lengths. We had earlier issues with the other architectures that some of the things they were doing better, the others they were not. So there are benefits of transformer architecture. We actually spent more time talking about it earlier, so I'm not going to go in too much detail. Point is that that is one specific way you can build it. I can add one more reason, which I mentioned earlier before we took the break. This is the most common architecture for which you have actually fairly stable frameworks available, both in PyTorch and TensorFlow. So if you are familiar with either of these two libraries or become familiar, you would get a lot of building blocks for transformer architecture available to you, ready to use. You don't need to write them from the scratch. Okay? Now, does anyone remember what does transformer architecture look like? We talked about it just a few days ago. I think it was Monday we did transformer architecture. Because everything we talked about, you have to implement somehow, right? So one of the important things as part of the learning is embedding layer. Okay, what the embedding layer is doing, it's converting whatever the input is into a vector representation. That's what embedding meant about. As a matter of fact, what the RAG or a retrieval augmented generation is doing is actually creating the embedding and inserting some additional data into the vector space of the model. It involves three processes. One is called tokenization. Now keep in mind, in an unsupervised learning, your base or foundation model does the tokenization for itself. But if you're doing that, or this step is actually common with RAG also. If you're building a RAG, this is exactly what you're doing. But in the RAG, you stop here. In this process, you're continuing further as well. So you're doing the tokenization. You define how the tokenization should work for your domain. We talked about earlier, why is not every alphabet a token? Why is it not the word is token? Realistically, as I mentioned, that the unsupervised learning of base and foundational model, it's been discovered that it's not just using the word as a token, but sometimes a part of the word as a token as well. Now, if you're designing it, you need to figure out what should your token look like. Subword token, 4 characters, 5 characters, what works for you? It all is like trial and error to figure out what is your token look like. Each token will get an assignment. If anybody has done compiler translator construction, this is a very similar thing. You create what is known as symbol table. This is very simple, similar to symbol table, and it's called vocabulary dictionary here. Each token is assigned a unique number so that going forward, that token is just a number, nothing else. Then you're converting that number into a multidimensional vector, which is what the model is doing when it's doing the unsupervised learning. Here, because you're doing it, you are converting it into a multidimensional vector based on whatever features are of interest to your use case. That's what the RAG is all about, and that's what the first step that you do it here. Make sense? Once you've got the embedding layer, which means the input data has been converted into a series of numbers or matrices of the numbers or vectors or whatever size you want, right? You might say that I want my vectors to look like 64 by 64, 255 by 255, or 256 by 256, whatever the case may be. Larger the size, more space needed, more training data needed, more time to train needed, right? Once you have that embedding layer, which means you've converted all the input data into a token, into a higher dimensional vector, what do you do next? you build the feed forward layer, which is where the neural network is calculating the incoming values and using the default weights and biases, and then percolating it through the entire network. And then after that, we'll do the backpropagation layer, right? So first you do the feed forward network. Basically what it is doing is that you need at least these two things, but you may need more. That's part of the architecture design. What is the feed forward layer is doing? You have a linear layer that is projecting into a higher dimensional space, which is basically the previous layer was. So first layer on the previous screen. So the first layer of your feed forward network is embedding layer, right? Which the work that it is doing is that converting it into the higher dimensional space. Then you need a nonlinear activation function. If you remember that when we were studying the neural unit or a neuron, every neuron needs a activation function. We looked at few of those. You can pick whichever way you want, right? There are choices. We talked about, I think, 4, but there are few more available. Which one should you use? It all depends on what is your domain, what you are expecting. Most commonly used function is rectified linear unit or ReLU layer or ReLU function. So you got the embedding layer, you picked up an activation function, and then you create the next layer, which is basically you're hoping that that higher dimensional representation is going to identify some hidden feature in the next layer. Do we need it? Not really. Why do we need it? Because generally we have found that this works. How did we find? We saw an example that if you just have one layer, you can only discover linear functions. If you want to discover nonlinear functions, implement something like exclusive OR, you at least need 2 layers. So you actually add a second linear layer. Now, in 2 linear layers will actually let your model discover nonlinear relationships and nonlinear functions in the data. So you do need minimum of 2 layers to make sure that your model does some realistic learning. Make sense? Now, because we decided that we are going to do the transformer architecture, does someone remember what's the next step in transformer architecture? So we described 3 types of transformers: encoder, decoder, and encoder-decoder. So the next step would be to figure out is that what are we going to do? Just encoder, decoder, or both? So I'm going to look at both examples so you can pick and choose depending on what your purpose is. Are you generating, translating, or whatever you're trying to do? The encoder layer should look like this. So you already have decided embedding layer. Then you're going to basically create a positional encoder. Now, why is encoder needed? Because you remember that it would eventually be doing the attention mechanism, because what we are trying to do, this encoder is looking around. If you remember that, there were encoders which were only looking at the data that you've already seen. There were encoders which were looking at both sides of the data. There were encoders which were only trying to predict the next one. There were encoders which were doing the masking, like they will hide some word or some token and then try to predict it correctly or not. So basically, you would need a positional encoder, a layer that's doing that. Sorry, is a question? No, okay. All right. Then you are trying to build a self-attention mechanism. The good thing that you have, those frameworks would actually give you functions to build this. Yes, you can tune them, but you have the functionality that's available to you. After the self-attention, there's a normalization layer. Does someone remember what normalization is? I did not necessarily explain it in the context of the self-attention mechanism, but we talked about in the context of probability density functions. Does someone remember what normalization was? You take a probability density function and make it such a way so that the mean becomes 0 and standard deviation becomes 1. Why do you need to normalize those functions? Because if you want to compare 2 functions, it's easier to compare them when they are normalized, which means they both have mean as 0 and standard deviation is 1, then you can compare them easily. So normalization layer is usually going to help you stable training because everything is normalized. So standard deviation is same, probability function is same. You can compare the output of the two, figure out the right learning or right response. You may repeat the same thing. If you remember that we said the self-attention mechanism, there is a stack of self-attention mechanism. Why? Because you want to enable the higher level features or higher level learning. So what I suggest that build at least 2 layers of self-attention mechanism so that you hope for that you have at least some higher level learning. So you started with two linear layers to make sure that you learn non-linear features. Then you said we're going to use the encoder architecture, which has at least 2 stack of self-attention layers as well now. If you're doing decoder or if you're doing both encoder decoder, so let's look at what the decoder layer will look like. Now the decoder layer would be, let's say this has the same thing up until this point. Encoder has already encoded some information. Now you need the encoder decoder self attention mechanism, which is really creating the relationship between input and output token, because decoder is generating the output tokens. More or less the same thing you are repeating, just that you have a different activation functions at the level of decoder. Does that make sense? So understand what has happened up until now. We figured out what the area we are trying to work with, the domain. Based on that and our understanding of the deep neural networks, we said that we're going to have an embedded layer, we're going to have 2 linear layers, we're going to have an encoder and decoder. Each encoder and decoder will have at least 2 self-attention mechanisms stacked one over each other. We are going to use, let's say, TensorFlow as the framework to do this. It has functions so that you can define your neuron. You can set up the neuron with an activation function. You define layers as these layers are. You make sure that you specify which layer comes after which one. So the output of one layer becomes to the input to the next layer. You've created your neural network. How good is that? No good, because you haven't yet trained. So really speaking, this network will have some default weights and biases, but not much. You may be lucky if those default weights and biases are of any use, but usually that's not how you create, or that's not why you created this. So now you have to think about running some learning cycles or some learning stages. For that, you need data. Now, you may have created, let's say, this kind of a network which has 6 or 7 layers. Maybe you say each layer has, let's say, 50 neurons each. So you've got 6 layers, 50 neurons, 300 layers. We're talking about a couple of thousand weights and biases, but you need the data now. Now, how good your network learns depends on how good the data you provided. So the data quality is very important. So you want to make sure that your data does not have inaccuracy in it. Your data does not necessarily have inherent biases in it, because we learn all of these things which are giving us a problem. There is some amount of predictability is built in the data. You're not doing supervised learning here. Neural network starts with unsupervised learning, but you do not want that your model produces incoherent or nonsensical answers, because one of the issues that you know that it's not easily known if your model is producing incoherent answer, insensical answer, that where is the mistake. I mean, yes, you're going to give it a try by changing the weights, biases, the activation function, introduce a more layer, reduce the layer. All of these are experiments because you don't know. I mean, there's a possibility. You start with, let's say, I'm just giving you an example, 500,000 words that you're using as a training material. Let's say you ran it, you spent like 12 hours training it. Now you gave it an input. Now, rather than expecting that it will produce like a chat GPT, like a response, it's giving you some gibberish. It giving you some nonsensical answers. There's no easy way for me to tell you that you're going to go change this, or this is where the mistake is. We don't know. It could be your data, it could be your learning, it could be your activation function. Maybe you're using the wrong number of layers. Maybe you're using too many layers. Maybe it's not. We don't know. We all give it a try. Poor quality data will actually either make you run the learning cycle multiple times. Keep in mind, there are also, I haven't talked about the tuning parameters yet. You may need to change the learning rate. You may need to change the other regularization functions so that you are generalizing it better. You have a lot of different tools to really organize. Maybe you need to increase the dimensions. So in the embedding layer where you're defining that, am I going to depict my knowledge in 5-dimension space, 10-dimension space, or higher space? Every time you increase the dimension, you increase the storage cost, you increase the training cost, you increase the cost of running the model itself. But you got to give it a try. High quality data, large amount of data is required to learn both linguistic and semantic relationships. Keep in mind, one thing I mentioned there. What was observed that semantic relationships are learned by the model only when it has a larger size, both in terms of dimensions, in terms of neurons, and in terms of the data. So if you want to get to that point, I mean, billions of weights and biases. But again, this is all learning, this is all research. Maybe you can come up with some combination of layers and neurons and functions which learn better than, let's say, ChatGPT for your specific use case. Yeah, it's possible. So usually the data curation is important, data quality is important. Some of the things a little bit in more detail what you want in a high quality data set. Keep in mind, if you are trying to build a model, you won't know how good your model is unless you can train it and use it. Other than that, it's a theoretical exercise that, oh yeah, sure, I created a neuron, I attached a activation function, I put them into layers, I created 3 layers linear, one self-attention layer, or maybe stacked 2 self-attention layers, got a softmax and got an output. Great. You learned the mechanics. You learned how to use and build a network. How good is it? You don't know unless you have a good data. You learned some good learning cycles, and then you're able to produce some realistic looking output. So some of it is repeat from the previous slides, but generally a high quality data set will not have inaccuracies. Keep in mind one thing I mentioned earlier. Large language models are not necessarily a good learner. They can't even learn as good as a 3-year-old baby. A 3-year-old baby usually learns most when they made a mistake. First time they touch something hot, you can be 100% sure they're not going to touch it second time. These models, when they make a mistake, they don't recover from it easily. They'll continue to make the same mistake over and over again. So you don't want inaccuracy, because if it gets into one inaccurate data point, there's a high likelihood that it will get more and more inaccuracies there. Minimal bias and harmful speech, clean data, no misspelling, no cross-domain homograph, spelling variation, contraction, punctuation. Any of these things can make your model confused. And as I said earlier, you can't just fix the model a little bit. You have to stop and start all over again, the entire learning, because we do not know which weight to tweak, which bias to tweak to make one spelling mistake corrected. So if you have one spelling mistake and you want to correct it, you have to restart the whole thing again. So make sure the data is correct. No duplicates, because duplicates can create unnecessary amplification of something that you may or may not require it. Privacy reduction, as diverse data as possible. The data should reflect the domain or the function of what you're going to actually use it for. So you may not want to take the data from history books and expect that it will work in the area of child psychology. I mean, it might give a totally, I don't know, inconsistent, inaccurate, or silly answers, right? So you never know what exactly is going to be. Once you've done all this, then let's get into the training part of it, right? What are the techniques that are available to you to run the training? We've got the network, we designed it, we've got the data, we've cleaned the data, we've got good quality data. Now, comes to the training part. There are a lot of different things that you can do in terms of the training. Some of it actually comes from very specific TensorFlow implementation. PyTorch has very similar, but it might be called differently or not. Because the training data actually requires, larger the training data, better your model will be. How many different network instances can you run? It depends on the hardware that you have. You can run one instance on each GPU. If you have, let's say, 8 GPUs, maybe you can run 8 different parallel networks implementation. Why do you want to do that? Because you want to speed up the learning process. Tensor themselves can parallelize. So what I'm saying here is that because TensorFlow is written to work on a vector, inherently it's parallel if there is an underlying hardware that it can utilize. You're trying to run it on your laptop, it won't be able to parallelize much unless you have more cores there. But those cores cannot deal with the floating point arithmetic, so it may not work better. It may actually slow down the whole process. If you have GPUs or TPUs or whatever the case may be, TensorFlow will automatically parallelize the computation that's happening. You can distribute the model across GPUs. This is the tough part actually. It's not an easy because you're not relying on the TensorFlow to do it. You're saying that I know my model and I'm going to distribute it I want. The framework TensorFlow allows you to do it, but you have to figure out more complex, more difficult, more error prone, but might be more efficient if you do it right. Okay? What can go wrong in the learning? Now, there are things which I briefly touched on because we didn't want to go too much into mathematics. There's a concept I mentioned was vanishing gradients. Now, that could be a problem in data, that could be a problem in mathematics because we're talking of these large numbers, small numbers. And we also looked at the optimization problem. There are two problems. The gradient checkpointing helps in both. One is that if you remember that rather than finding the minima, it starts oscillating, right? You want to check for that. You also want to check when the gradient becomes 0. Then what happens once one gradient becomes 0, eventually, as I said, that model is a bad learner, it will in a few cycles make all gradients as 0. Which means it's a clean slate now. You keep running it for another 100,000 cycles, it's not going to make a difference. So you want to do the gradient checkpointing built in. Think of it just like writing the printf statements, just that each statement will print like hundreds of thousands of weights and biases, which is what the gradients are. So you want to do some checkpointing to figure out those two problems. It's not oscillating and it's not vanishing or becoming 0. If that happens, what do you have to do? You can go the extreme. You can change the architecture of your network, but that's the extreme step. You have some more tuning parameters if anyone remembers, right? The regularization parameter, the learning rate, the temperature, the size of the batch. There are quite a few things. Any change, you have to restart the cycle of training, but you need not make the change in the architecture of the network. So you have these hyperparameters which you usually set before training, does not change while the training is going on, but if you run into problems, then you change these hyperparameters, go back, like a training behavior. So that's the exercise that you do in trying to get to a point where you have come up with an architecture, got the data, have the learning cycles run, making the checkpointing in between so that the gradients are not vanishing. Usually speaking, and I mentioned this earlier also, you don't use 100% of the data that you have available for training. Usually you use 80% of the data. Use the other 20% to validate, is it generating the same output, right output, sensible output, meaningful output. A lot of time you would see that it's called mini batching, whereby you're using the same data multiple times by creating the batches of the data so that you can, even though you have, let's say, 100,000 words, you could create batches so that you transform this 100,000 words in, let's say, 400,000 words because you create different batches. Once you have done all that, then you know that you can test your model. Again, both TensorFlow and PyTorch lets you create the conversational agents, which will help you have a similar to a ChatGPT-like interface. Rather than OpenAI's ChatGPT, it is interacting with your implementation. Okay, so I think one of you asked for it, how do we do the practical way of doing it. Now, obviously, we never started this course based on that because I wasn't sure how exactly we were going to do. So what I mentioned there was that this is a book which comes from Harvard professor, mlsysbook.ai. Has anyone heard of it, seen it before? It covers mostly the same topics that I covered here. Two other things. One is that it also looked at some data science topics. It obviously goes in more details than we did here. The entire book is available at this. It's an open source. So if you see here, there are some essential topics, which is usually what I covered actually. And then it goes into engineering principle, which I presume most of you should know. Frameworks, training, efficient AI, model operations. Some of it is common with software engineering. Some of it is specific to AI. And then it goes into some more advanced topics or research topics. I expect that you should know most of what is in the first 4 chapters and maybe some portions of some stuff here in engineering principles. We didn't talk that much about engineering principles. You go to the site and then you will see a lot of detail. I would strongly encourage, if you want to get more and have hands-on experience, then you do that. They do have references to TensorFlow framework to say, if you want to do this, how exactly you would do it using TensorFlow. So you can make it work here. A few things that this book does, basically, it talks about data engineering, it talks about model development, optimization, which is where majority of your effort will go, fine-tuning model performance, because you don't want it to be trained and give you garbage, right? Deployment options, monitoring and maintenance. I'm not sure if that's what your intention is. These models, just in themselves, creation and training will take a lot of resources. I mean, either you need to have your own machine with some GPUs on it, or you would need some network to do it, unless you're just doing pure data, right? So what I'm going to do, and very quickly, has anyone used TensorFlow here? Okay, a couple of you. So you might find it, there's some modules of TensorFlow, data, core, light, serving or extended, which is going to map with what the book is referring to, and in turn of whether you're trying to do pre-processing, model creation, training, optimization, it will give you some hints. TensorFlow, I think it's very well documented. You should be able to use it. The only problem what you run is that it's very late in the process that you realize that you made a mistake, because you have to create the model, you have to create the layers, you have to run the training, and then only realize that is it producing the expected output or not. So make sure that you learn, and you learn by making mistakes. You're not the language model, so the failure should be the best friend. Fail fast, fail quick, but learn from it and not repeat it. That's the mantra, right? So just to summarize what we said earlier, figure out the use case, make sure that you have a model architecture. You can start with, I mean, listen, this is one thing again, which is there is no science yet, in the sense you got to figure out what works best for you. There are some suggested hardware. You can make copies of what's published for Llama, what's published for BERT, what's published for a lot of different published articles. They'll tell you that what layers they used, what size of the neurons they used, what's activation function they've used. Most of it is published information. I shouldn't say most. Most of it is published information for open models, let's put it this way. You may not replicate the number of neurons, number of layers, number of dimensions, because you require a lot of hardware, but you can give it a try. Then you got to train with the right data, and then only figure out whatever you did was worth doing it or not. Okay? So basically we covered all the building blocks. We didn't obviously try by hand, but I think you'll find this book interesting. And because it links to TensorFlow, you'll find it usable also. I suspect if you have done this course, if you have paid attention here, you start working on it, let's say next Monday, you should, and if you have a decent machine, you can implement or at least give it a try in 1 week itself. You should have something up and running. I can't guarantee it will give you the meaningful answers. It can give you gibberish, it can give you something else. Try doing it. Try building a translator, English to Hindi, Hindi to English, or something of that nature, so that you can actually experiment. Why I'm saying that, you can actually provide some meaningful data. All you need is Hindi and English translation in sentences, or any other language, Indian language. If you can build a data set for, I would say, 50,000 sentences, simple sentences, one language to the Hindi to English, English to Hindi. Create a simple architecture. 2 layers of attention should be enough to do that, and then see if it creates some meaningful answer. I mean, you would be able to test it easily, right? If you're trying to do remote sensing, that's very complex, very kind of resource intensive application. But if you can make a simple sentence, I would love to go to market and see if it translates in Hindi, or the other way around. You can figure out, right? And you can learn the techniques that by tweaking this worked better. By tweaking that worked poorly. So that was just one example, but you can start doing something else. You can start training it on, let's say, articles written on politics, say if it can summarize it. I mean, you can deal with some of smaller problems even if you have a smaller data set. But again, the translation is one thing. That is probably something that you can very quickly determine whether it's working fine or not. Then try to make it more difficult, like trying to say that my bank is on the bank of river Ganges. Does it figure out which bank is referring to which bank as a semantics thing? You can make it more complex. My point is that if you take that as an example, you can create data sets, you can introduce the complexity slowly and see how your model responds to it. Once you have it, try doing the prompt engineering and see, and you will notice that if you introduce some things as a supervised learning later on, how does it work? Does it do well? Does it not do well? Etc. etc. You can give it a try. So, again, in the time frame that we had to cover the introduction, we had to cover the non-technical topics in terms of the costs, benefits, risk, weights, biases. There's one topic that I have not covered, which I'll do it tomorrow, which is regulations, the rules, regulations, laws, and how in India it's happening, right? That was something which was supposed to be done yesterday and today in combination, but that's fine. We added something new, which was of interest here. Any questions?
What is the difference between a PyTorch and TensorFlow? And when will you use a PyTorch or a TensorFlow?
Okay, now that's no. That's a question like that. Do you want to use Java or Python? PyTorch is a Python library. PyTorch came from Facebook, roughly, or Llama or Meta, basically today. TensorFlow comes from Google. TensorFlow has several languages interfaces. I don't think it has Python. I may be wrong, but you can use Java. You can use some of the other Google languages. What is the other language that it has? Does anyone know what the language that Google is using nowadays? It's skipping my mind. It'll come to me. So Google has a new language which they are using. It's kind of C++, but better. So you can use that. So I can't tell you which one you want to use. These are the frameworks specific to the language, and they are from 2 different sources. Both are in public domain. So if you are a Python developer, let's say, you think you are much more comfortable with Python, I would say go with PyTorch. If you are okay with Java or any of those languages, then go with TensorFlow. TensorFlow has one built-in advantage that it has parallelization built in, because do you know what the tensor is, right? Vectors and tensors.
Mathematics.
Yeah. Yeah. So what is it? It's multi-dimensional, basically. So it can parallelize. Yes. N-dimensional space, yeah. Tensor is used to represent n-dimensional spaces, so that's what it is. Any other question? Okay, you were going by, I think one of the slide has it somewhere, right? Which one was it? Yeah, data curation, yeah, which is where I was. Where exactly have I used it? No, not in this. This was one here. No, it's here somewhere.
Filter for boilerplate things.
Okay, I don't see it here, but usually the boilerplate text actually. Let me give you the history of boilerplate. Has anyone seen old style printing presses? Sorry? In movies, right? Where each paper was like a big plate, each page of the paper. So the term boilerplate came from in the sense that, let's say the front page of a newspaper, there are things which change, there are things which usually do not change that quickly. So boilerplate is also known as, like in some cases, pro forma. Those who are doing finance or management, they will know pro forma statements. Now pro forma has slight differences. Pro forma is also, part of it is like fixed, or part of it says that pro forma means things can change. So boilerplate came from two places, printing presses or anything mechanical. Things which are not prone to change are fixed. So for example, you would see in the old area, and if you look in the movies, the plate is ready, pro forma, or boilerplate is ready, you're just going to fill in a few details. The must page news item is ready, but the title is not there or headline is not there. So that's called boilerplate. The reason why we say that you don't use the boilerplate text is that it does, because by nature it's not changing, it's relatively fixed. So theoretically you might be saying I have this much training data, but if 80% of it is boilerplate text, there is no new learning that is happening there. That's what is meant by the boilerplate text. Okay, any other question?
So in one of the slides says the word contraction was stated. What's the layman's understanding?
Which one? Oh, sorry, what was?
Contraction.
On the same slide? Okay, all right. So that helps. So you know something like, for example, cannot. That's what the contraction is. So what we were saying is that avoid this in the initial learning. So, or any other contraction that might be used. Like, you guys have used it. PDF. Okay, it was used yesterday in the departmental meeting, like postdoctoral fellow. Yeah, if you write PDF, what will the model learn? So the reason we're saying is that use clean data. Don't use these contractions or the words which are more common here. I mean, you go tell an NJIT that, is there a PDF opportunity here? People will say, what exactly you're talking about? I have no idea, right? So don't use those kind of words, basically. All right, any other question? Yes, no, maybe? Okay, if not, then when we meet tomorrow, we're going to talk about policies and regulations to some extent, because that's what we said we were going to cover as the course was put in design, and the status in India as to whatever is happening in India. I may not know all that is happening in India, so I'll rely on some of you if you have an interest, especially if you were trying to do research or trying to get in some areas which are relevant to you. But that's what we're going to cover. In addition, I'll say that if anyone looks around, get into the TensorFlow or in the book, and if you have a question, if there's time permit, we can talk about it. We can have some conversation, discussion if anybody has an interest there. Okay? All right, guys. Great. Thank you.
Good afternoon, everyone. My name is Shubhi Changani, a research scholar working under the supervision of Dr. Rakesh Kumar. I am doing PhD from SMS MNNIT Allahabad. And before starting the presentation, first of all, I would like to take a minute and extend my gratitude to Professor G.P. Sahu, sir, for organizing this wonderful workshop, and also Prabhat, sir, for taking such insightful session. Definitely these 2 weeks were a good opportunity for all of us because we learned a lot, explored about AI, and also share our ideas. We got to know how this AI, generative AI, is transforming our lives. So basically in today's presentation we will be talking about text generation using generative AI. And these are the name of the team members. They all have contributed their efforts and time in making this presentation by editing or merging the slides, or some of us are presenting today. So they all have worked for this. So text generation using generative AI is a fascinating technology that allows computers to create human-alike text. How text generation works is that it analyzes a lot of data which we are only providing by searching or learning using internet. So AI learns how people write and then uses this knowledge to generate responses, stories, or explanation based on what people are asking, whether it's completing sentences or answering questions or even writing creative content. And therefore this technology is transforming industries, making communication faster, smarter, and more efficient. So in this presentation, overall you will get to learn how text generation using AI is helping and transforming industries.
Good afternoon, everyone. Now we start with the introduction of generative AI. That what exactly the generative AI is. So it can be defined as a deep learning models which is used to create contents, text, images, videos, or audios. The next come, what are the applications of Gen AI? That for what we can use Gen AI. So the Gen AI can be used for image creation, text generation, music composition, and drug discovery. Moving further, what is text generation? Text generations are large language models like generative pre-trained transformer, which is most commonly known as GPT. And they use the deep learning techniques to understand the structure of sentences and generate coherent and contextually relevant text. We can use, what are the real examples of text generation? We can use text generation for content creation, chatbots and virtual assistants, language translation, and summarization. The next will.
Moving forward to innovation in text generation. So basically, what is the innovation? Anyone? So innovation is development and application of new technology model approaches that enhances the ability of the system which we are working on. So moving forward, I'm going to talk about the transformer models. It has revolutionized the text generation by enabling better context, understanding, coherence, and fluency, which I have mentioned only. It basically works on the principle of self-attention and positional encoding, in which we are giving the positional encoding to provide information about the positions of the text so that it enhances the text according to their differentiations. Now, moving forward to the personalized and contextual text generation, which means that it involves adapting a generated text based on user-specific information and ability to generate the text that is relevant to the current situation. It based working on user profile, behavioral data, and temporal and situational data, which is the major working of the same. Now, moving forward to the real-time interaction and responsiveness, like we have used ChatGPT and other. So, what are they doing? They are innovations enabled that to give the real-time interaction to avoid the frustration which people are having using the same. Moving forward to the ethical text generation, the major part And the major drawback of the AI is that what about the ethics? So the innovation in ethical text generation includes addressing bias, content moderation, multilingual capabilities, and zero shot and few shot learning.
So now we'll see the disruptions in text generation. So before moving ahead, let us understand what is the meaning of disruption. The generic meaning of disruption is interruption or breaking the normal course of action. But here in the context of text generation, disruption is often refers to innovation or a significant change in how the text will be generated or consumed. So let us see some of the key disruptions in the field of text generation over the time. So basically this slide and the next slide, both slide talks about the AI, artificial intelligence, and NLP, that is natural language processing. So in short, artificial intelligence can be defined as a simulation of human intelligence in machines, so that the machine can act as a human and take the important decision where there is a need of human beings. And on the other hand, NLP, that is natural language processing, it's a kind of software which enables the machines to understand the natural language, that is the human language, in a more efficient and better way, and can respond accordingly. So overall, altogether, the AI and NLP talks about the transformer models, that is GPT and BERT, B-E-R-T. So they have completely transformed the text generation field by understanding the context of the text in a more better way and giving the response like a human beings. Also, the artificial intelligence can do the tailoring of text and can give the response to the users as per their requirement and preferences. So over the time, the technology improved more, advancement in the technology happens more, and with that we have voice interfaces and conversational AI with us in between us in our system. So let us understand this slide with a very simple example. Nowadays we have Alexa, Siri, and chatbots in our system. So what they do is they can take the input in the form of voice, also they can give the output in the form of voice. So this has made the text generation even more simpler for those who don't know the technology and typing skills. Now the rise of no-code text generation platforms. So earlier to generate the text we need to do the coding. So it requires some technical skills. Not everyone can do the coding and can generate the text. But nowadays, as the technology evolved more, we have no code text generation platforms with us. So so because of this, more number of people can be covered under the umbrella of text generation. Also, this has increased the productivity because no more coding is required. Now, in particular, this slide, I have tried to explain the future of text with the 3 points: collaboration, augmented writing, and human-centric AI. So the future of AI totally depends on the fact that how we are going to collaborate the human skills with the artificial AI. That the human skills means the emotional and creativity skill of human beings, and the speed, accuracy, and vast knowledge of AI. Augmented writing, the AI can act as a tool for the writers and authors, and the AI can do the augmented writing as well. And the last one is human-centric AI. So in future, whatever the improvements in AI is going to happen in context of text generation, that will be going to happen by keeping in mind the ethical and moral concerns of the human beings.
Good afternoon, everyone. OpenAI is the evolution of text generation. OpenAI is a company which is pioneering in generative AI, and Google which is powering NLP and AI, and Meta is expanding AI capabilities, and Hugging Face, which is a company which is democratizing AI, and Anthropic is a company which is contributing to safe and helpful AI. Timeline of text generation advancement. It is started in 1950s and ends in 2023. OpenAI, it is started in 2015 with a mission to ensure that AI benefits humanity, and its key model is GPT-3 and GPT-4. ChatGPT is a user-friendly conversational AI that has been widely adopted for personal and professional tasks. And its innovation is OpenAI made this model accessible via APIs, enabling businesses to integrate advanced AI into their products. Google, which is founded in 1998 with AI research gaining momentum after 2010. Key model is BERT, which is introduced bi-directional transformer, understanding the context in both directions. BARD, Google Conversational AI, built to rival OpenAI GPT model, integrating with Google vast search engine. Innovations: bidirectional attention mechanism, revolutionized NLP understanding, improving search relevance and contextual analysis. AI-driven Google search and cloud tools such as Google Doc and Google Translate. Meta. Meta is founded in 2004, which AI research evolving in late 2010. Key model is Llama, a set of open source model focused on democratizing AI. Blender Bot, a chat bot built on deep learning models with an emphasis on generating conversational, context-aware dialogue. Innovation. Meta commitment to open source AI model, encouraging collaboration and innovation across AI research community. Key player compared. OpenAI key model is GPT series, Google is BERT T5 BARD, Meta is Llama, and Meta focus area is OpenAI, open source AI. And Meta's market approach is open source, and Meta's market impact is medium.
Now for the regulating text generation, regulatory aspect of text generation includes empowering and establishment of guidelines, rules, policies to ensure that AI is used responsibly, ethically and safely. And for this, the issues like preventing misuse, mitigation bias and ensuring transparencies are done using regulating text generation. This is the essential why regulations are essential. 4 basic points: ethical compliance, accuracy and reliability, legal adherence, and trust building. These are the key areas of regulation: context moderation and harm prevention, accountability and transparency, data privacy and ethical use, bias mitigation and fairness. Moreover, further consideration are use case restrictions, monitoring and enforcement, public awareness and educations. And these are the challenges and part recommendations for regulation aspect of text generation. These are the key challenges: keeping pace with rapid advancement in AI technology, addressing global difference in law and cultural values, balancing regulations with the need for innovation and creativity. And for the recommendation, fostering international cooperation with uniform standards, implementing regular audits and public awareness campaigns, promote ethical AI practices in development and deployment, and lastly, the effective regulation ensures generative AI benefits society while minimizing risk.
Now I would like to saying something about impact of text generation. Text generation in AI has a significant impact by increasing the efficiency of content creation, enabling personalized communication, improving accessibility through language translation, and facilitating human-like interaction with machine. And it also raises some concern about potential misuse, such as fake news propagation and ethical issues around originality and authorship. Key impact of text generation in AI is increased productivity, personalization, accessibility, creative potential, enhanced customer engagement, language learning support. And now impact of text generation in management domain. In management domain, text generation is used to create written content for manager to efficiently communicate key insights, analyze data, streamline administrative tasks by generating human-like text based on complex data set, saving time and improving decision-making process. Key applications of text generation in management is data analysis summaries, meeting minutes, performance reviews, customer feedback analysis, email drafting, project status updates, increased efficiency by automating repetitive writing tasks, freeing up manager time for strategic decision making, improved communication, data-driven insights, and personalized communication. Thank you everyone for listening our presentation.
Good work done. Okay. So do you have something more to say? No. Okay. So it's a comprehensive work. I believe Professor Vaish will agree with me. So I also used to say in my regular class also that teaching learning, if you do chalk and talk, retention is around 20%, 30%. When you do on your own, retention is going to be very, very high. So up to, if you do on your own, so retention is going to be 100%, possibly no 100%. So now I believe all 14, 15 number of people who have participated in this discussion, text generation. So I'm sure all of you have experienced good learning, and then you'll retain it for maybe forever, okay, and then keep on building it. Any quick question before I request Professor Vaish to say something about it? So any quick question from group 1 and group 3 to group 2? Anything you would like to know about? I appreciate the work done by group 2 and comprehensive presentation of course they have made. Certain limitations also are there, so those ethical considerations are also there. You try to attempt, you presented that. That's great, okay. So any quick clarification needed? No? Okay. So Professor Vaish, would you like to say something?
Let me have all other
three and then your input. Yeah, should be fine. So next, group 1, ready? It is not a competition, so all participation is very, very important. So if you participate, it's going to add to your learning experience, okay? जरा help कर दीजिए presentation connect करने.
A very warm welcome to everyone. My name is Durgesh, and I'm a computer science undergraduate student at IIT Ahmedabad. So I would like to thanks to the GIAN initiative, which allows me to represent my presentation here, organized at MNNIT Allahabad. So before diving there, let me ask you a simple question. How many pictures do you have of yours, of your grandfathers, or of your grandfathers? Perhaps you may have not the exact pictures because the technology and the cameras have not that much evolved. But you definitely have some attributes like how they look like, what their facial structures, heights, and their body structure. So now, is it possible to reconstruct or regenerate his pictures? Perhaps up till 2010 it was not possible, but now it's possible just because of the advancement in technologies which brings like generative AIs. So let me introduce you to my topic, that is image generation through generative AI. Before diving further, let's have a quick intro to what is exactly generative AI is. So it's an AI model, works on different classes and complex structures like neural networks, which is being responsible for creating new contents, images, videos, and text based on the data which it has been trained, or based on the input or the prompts which is being provided by the user. So if we talk about how the generative AI evolved, or how the image is being evolved in the computer, so it was started in the early 1950s to 1980s when the conceptual beginning starts. We have algorithms to generate complex images, but are used to generate only simple patterns and drawings. There are also landmark programs enabling users to draw a computer screen, laying groundwork for computer-aided designs. And the revolution started to begin when the graphic cards being introduced in the years of 1980s to 1990s. Algorithms like fractals were used to generate the complex, natural-looking images such as the landscapes. And these systems relied on predefined rules, not on learning and adaptability. That was a major constraint because it was learning from the data, not exactly generating that much extent which we needed, just because the GPUs and hardwares are not that much developed at that time. Now, emergence in machine learning was a second most important step before the deep learning comes. So it was the year 1990s to 2000s when machine learning began to influence computer vision and image generation. The concept of simple feed-forward neural networks and early conventional neural networks were exploded for pattern recognition, but had a limited success in generating tasks. Whereas image generation focused on transforming known patterns, often using human designed filters and transformations. It was the year 2010 when the deep learning came to the picture, which has the ability to recognize and learn from the pre-existing data, which was not only step-by-step following. The advanced image recognition capabilities led to the interest in generating task architectures like AlexNet improve understanding of spatial data. There are the two most important Gen AI programs like the GAN, which is Generative Adversarial Network, and somehow there are diffusion models and encoders and decoders, which has improved the technology a lot. So advancement in generative AI models 2015 to 2020. The lots of GAN architectures were improved, enabled tasks like image-to-image translation, creating photorealistic human faces, and controlled images attributes. There are the reinforcement learning and creativity, which cross-verifies the image by the user that whether it is being generated well or not. So models explore generating arts and designs inspired by human preferences. Recent breakout was 2020's Transformers in Image Generations. DALL-E by OpenAI was introduced and inspired by human was a transformer-based model capable of generating images from text prompts. It was the first time when it was image being generated from the text formats. There was a clip in 2010-2021 combined version and language understanding, enabling refined text-to-image generation. So we have diffusion models, stable diffusers, DALL-E2 and Midjourney 2022. Diffusion models images as a leading approach for generating high-quality images, offering controls and coherence. Generative AI ecosystems, tools like Adobe Firefly and many other editing tools have collaborated or introduced the AI in the system so that editing can become enhanced and more realistic editing can be done. Now the principle of image generation, we have generally two most important and successful principles. These are the generative adversarial networks, which consists of two neural networks, discriminator and generator. One creates the images and other cross verifies whether it look like real or more look like artificial. Diffuser models produces noise in the image and try to denoise the model to gain the original data sets so that the final result that we get should be a best possible one. Now the further slide will be carried forward by my friend.
First of all, good morning everyone. Thanks sir and most respected teachers. My name is Karuna Shankar Prajapati. I am from IERT Prayagraj. The next topic is innovation in image generation. The field of image generation through AI in a prime example of technological innovation. Key innovation includes examples like DALL-E, ChatGPT. Innovation in image generation, speed and scalability. AI image generation can drastically reduce the time required to create high quality images. Faster production cycle for industries like video games, film, marketing. Artists can generate several variations in minutes. Creative assistance. AI model can serve as a collaborator for designer, providing them with initial drafts or design ideas that can be refined further, making creative process more accessible and efficient. Customization at scale. AI allows personalized design at scale, whether it is generating individual avatars, custom products, design, or targeted advertisement based on user data. AI creative assistance. AI model can serve as collaborator for designer, providing them with initial drafts or design ideas that can be refined further, making in creative process more accessible and efficient. Customization at scale. AI allows personalized design to scale, whether it is generating individual avatars, custom product design, or targeted advertisement based on user data. Disruption in image generation. Impact of artist and designer. AI has advanced more with the respect of time. Traditional roles in the design, artist and photography are being challenged. AI can replace artistic styles, automatic tedious process, and reduce the need of manual intervention in the certain tasks. Creative industries. Creative industries can innovate AI. In the entertainment sector, generative AI can detailed environment, characters, and visual without needs for costly human labor, potentially lowering the barrier to entry in smaller studies. Stock image market. The stock image industry has been seen a shift as AI generated images can replace traditional stock images, photos, offering more variety of customization without licensing concerns. Cost reduction. Traditional image creation process, example manual photography, illustrations, requires a significant time and resources, where AI generated content can be lower these costs considerably. Incumbent in image generation. Incumbent player, creative media and design industries are responding in several ways. AI image generation, adaptation and integration. Major design software companies like Adobe and integrating AI driven tools, their platform offering generative features like Photoshop, neural filters, and Adobe Firefly, enabling creators leverage AI in their workflow. Resistance and ethical concerns. Many traditional artist designers have expressed concerns over the ethical implication of AI generated art, including the potential for job displacement, the challenges in defined authorship and ownership. New business models. Companies are shifting their business model to accumulate AI generated content, either by embracing AI tools for efficiency, providing service around curation and regulation of AI generated content.
Good afternoon, sir. Now I am continuing this presentation. Regulation of image generations, copyright and ownership. Who owns AI generated images? The question of authorship, whether it belongs to the AI's creator or the user of the tools, remain a gray area. There are some issues like ethical issues, bias and discrimination, privacy concerns, accountability and transparency, job displacement, ethical use in surveillance, and legal issues, data protection and privacy, intellectual properties issues, and liability and accountability issues, cybersecurity threats, and use in governance and policies. Here, data security. Data privacy is a major role. Since AI models are trained on the vast amount of the data, including publicly available images, ensuring that the data used in the ethical source and does not infringe on the privacy rights is critical. Impact of image generations, cultural and social impacts, economic impacts, education and training impacts, and legal impacts. The future scope of the image generation is improved realism and details. As AI model continues to evolve, the quality of generated image will become even more the study from the real photographs. employing hyper-realistic visual environment and characteristics and products. Personalized AI-generated content. AI could tailor image of the specific needs and the preference of users. Obviously, highly personalized designs avatar of marketing materials, which will be increasingly relevant in the sectors like retail and e-commerce. Interactive design tools. The future may see AI working alongside humans in an interactive way, where users can provide continuous feedback to refine and improve generated image in real time, enabling co-creation between the humans and the machines. The conclusion, the AI-based image generation has already started and transformed the way creative industries operate, driving both innovation and disruption. As the continues to evolve, it will further impact industries, rise regulatory challenges, and open up new venues for creation and expression and the business opportunities.
So, good work done by team 1. We appreciate. Again, I would like to ask if you have any question to ask. Team 2 and team 3, would you like to ask any question? This is again a very, very creative work, very well prepared and then delivered. Special thanks to him as well, being UG student there. Yeah, you're pursuing your UG. So you're doing excellent work, okay? So lot of appreciation for it, okay? So by the time you fix up, I wish to further mention, like those who are from city Allahabad, you might have seen this Shaheed wall. Have you seen it? No, opposite to Hanuman Mandir, there is a Shaheed wall, okay? So what they have done there, they have identified who are the Prayagraj people participated in freedom, for the freedom, and they sacrificed their life, okay? So few pictures, few statues, if you see there, so नीचे लिखा हुआ है कि 18 साल की उम्र में शहीद हो गए, but picture if you see, it is not appearing to be 18 साल, okay, 18 years, okay. So that there maybe your role is very, very important. That of course we need to, people know that their attribute, how the face was looking like, how old they were, and then how the physique, healthy, not healthy, but some improvement of course is needed. I recommend you to visit there, Shaheed wall, income tax office ka wall hai, so there it is, okay. But you'll very easily you'll be able to identify the faces, and then faces are not matching with the attribute given there. Few cases, okay. So one case very clearly we observed, only one case that it is not the case, okay. Then many cases you also presented that people are losing job, okay. Models now, okay, those who are demonstrating or advertising for a few of the products, okay, so they are also extensive use of this image, virtual image creation. And then in case of or the worships, okay, so Ramji ki murti or Sita, so there also more and more attributes, value added pictures we are getting, and then we are happy with that, okay. So if no question, can we shift to group 3? Okay, so over to group 3. Thank you.
Well, hello everyone. We're group 3, and firstly I would like to express a degree of gratitude towards our course coordinator JP Sahu sir and the professor in charge Prabhat sir. Sir, we would just it's not a scripted thing, but we are truly grateful for the invaluable lessons which you've inculcated over the past few weeks, and the degree of depthness into the topic, sir. We are truly grateful for it. Now, getting into our presentation, we'll be discussing the future of music industry with context. So we'll be discussing the future of music industry with the inculcation of generative AI. Generative AI, firstly, is a subset of artificial intelligence itself. In a very layman's term, it deals with how the music industry would be revolutionized with the introduction of AI into it. Now, getting into the different subsets of it, my friend in charge would take care.
Good evening, everyone. as I have to talk about the innovations that are going on with the help of Gen AI in the music generations domain. Nowadays, Gen AI is helping every domain to getting revolutionized. And if I talk about the music composition, Gen AI is helping in many ways. Like if we see that we use music only as our entertainment purpose, but Gen AI is not helping us to make sorry make music to entertain in much better way. But Gen AI is also helping music in medical sectors. Means Gen AI is making music more better to help in medical sectors. Like many patients of dementia, they are getting treated with AI created personalized soundscapes, and the neurofeedback integrations is also are the points that are getting done with the Gen AI, with the help of Gen AI. And as I said that we are most of the case we are using the music for our entertainment purpose. Then Gen AI is also helping in that portion, that we are now able to compose the music according to our personal desires, like emotionally driven tracks and interactive experience. And nowadays, the Google's Magenta project and OpenAI's MuseNet, these are the two main platforms that are not the main, but they are the biggest platforms which are helping persons in the music domain. That nowadays the persons who are not the professional songwriters, composers or singers, they can compose their own songs with the help of Gen AI tools. And with the help of Gen AI, we can also generate the music that has been lost in historical cases. And we can also and if I talk about the disruptions in music composition, that nowadays with the help of Gen AI, we can make any type of make songs much better than the humans. It is the biggest problem for nowadays the humans, that they are getting the competitions in the music industries. And many labels and many companies, they are nowadays preparing different songs or making different songs, and they are not able to public them because of the copyright issues. And they if they publish on any platform, then they have the problems that different songwriters or the composers which have already worked on that song or on that domain in the past, they also sue them on the copyright issues.
Okay, so good afternoon everyone. First of all, I would like to show my gratitude to all the team members who has contributed in creating this presentation. And next topic here is incumbents and music generation. So now the music labels or music industries are adapting AI to AI music labels. Adapting AI for generating or composing music in the from now onwards. So for this, they are investing in AI technologies. Labels, music labels are funding research and development to incorporate in AI tools and their workflows. So So these AI tools or this generative AI is used to analyze the streaming trends and to predict the hit songs or any other songs, and to optimize the marketing campaigns also. So some companies which are adapting all these AI tools or adapting generative AI in music composition is one of the most renowned company is Warner Music and also Universal Music, and these both of these music labels are investing in startups to explore new ways to generate new music or generate revenues while protecting the intellectual properties of the music. And for AI and these AI companies are innovating in music creation and distribution also. So these are some of the companies like Newbert, Alibaba, Nvidia, Sony, IBM, Microsoft. All these companies are trying to compose new music in the industry, and these are leading AI music composition companies like Suno AI, SoundDraw, Newbert, and now he will continue.
Well, thank you for giving me the central stage. Now we'll be discussing the regulations in context of generative AI. Firstly, copyright claims. With the advent of so many of AI-based tools, it is actually very difficult to pinpoint to the extent, to the mindset, to the paywall, to what extent a thing should be copywritten, what the degree of originality is quite ambiguous. Secondly, privacy concerns. The music generated by AI, what we should keep an emphasis on, that should not include any personal information of any individual or an organization without their prior consent. Lastly, fair use. The fair use is an umbrella term consisting of a holistic segments which includes both the copyrights and trademarks policy as well as the privacy concerns of it. Then the impact of generative AI on music. Firstly, new sounds. The generative AI has enabled even the newbies or what we call the noobsters to generate a music of their own. Like, taking a break from this, some of the Gen Zs in here must be familiar with the artist called Rustage. He usually sings songs from the Naruto and other animes. So that the degree of that music is almost unmatched from any real world artist or a creator. That's the biggest contribution which AI has in the terms of music. Secondly, increased accessibility. Prior to AI, music was an industry which was mostly a natural talent based thing. Either you are good at singing or you're not. However, tools such as AI based auto tuning tool has increased the accessibility of music generation. Lastly, evolution of music. AI has enabled us to even track back an artist's performance like a decade or two from now. Like, even if Lata Mangeshkar had died, with the use of her voice sampling, we can generate new songs in her real voice using AI based tools. Yep, that pretty much summarizes it all. Lastly, what our collective take is, yep, AI should be used in the music industry with some degree of caveat, such as there shouldn't be a breach of personal privacy, there should be a clear boundary to the copywritten and trademark policies, etc. Yes, sir, that summarizes it all. Lastly, I'd like to extend a gratitude towards our team members as well who are sitting up there.
Thank you so much, everyone.
Okay, so thank you very much, Team 3, for doing it. Any question? It's a great work again, like music, songs, even audio. Day 2, we were talking about Candy AI, their AI companion we talked about, or Hello Mumbai, okay, radio jockey. So radio jockeys can also be replaced with AI jockeys, okay, and they may be doing Great work, okay. So any quick clarification? Team 1 and Team 2, all team have done excellent work. So now, over to you, sir.
So, one question. So everybody contributed, right? So in a way, everybody was part of one or the other team. Is that right?
Yeah.
Okay. All right. So, couple of things I'll say that. So, great work, everyone, and you picked up the topics. One was image generation, music. Yes, good work, all of you. So I'll say the couple of things in the sense that, so I think you covered the pretty wide range of details on each of these topics. I was happy to see the legal issues, ethical issues, technological issues as well, right? And given the fact that a couple of you are undergrads, some of you have no technology background, so I think it's a good mix, right? My goal would be that you take it from here forward, and whatever you learned going forward or whatever you do going forward, see if you can apply this, because I think that's very great. So good work overall, good presentation, and it covered almost everything that we discussed. So great work. Good job.
Yeah, okay. Ready? So can we break? Now still we have 4 more minutes to go, but no question, then we break here. And not break, you may leave, but food is there in the outside, it is arranged, so go take your food, okay? Okay, so see you tomorrow morning, 9:30 again, and tomorrow's schedule is known to you, okay? Only 1 hour teaching, and followed by 1 hour teaching examination, then valedictory, and feedback also please be prepared with the feedback. Okay, so you may. You're up. Close.